It's very speech.
Please. Okay, good morning. I will offer you a more or less a long presentation. The activity that we did together and what we will do in future. So this outline of the presentation. First of all, let's to introduce our laboratory. It's a laboratory for signal processing and measuring information. We are in Benevento. Where is Benevento? Benevento is in Italy, and Benevento is a town between Naples and Bari. It's the central south part of Italy. It's a UNESCO town. It's older than Rome. So the people living there were destroyed in a war, Salitic war by Romans. So is a old, very old town full of monuments for the people. Some of you already visited the town. About my research group, this is we are 12 people. In particular, I wish to inform you, highlight that 4 of them are PhD students. 1 from Pakistan and 2 from Iran. One of them is working with the NATO project. So it's another strange situation. Please, if you are a student or you are a professor that wish to send us PhD students, we may accept them. I think that we may collaborate with the Moldovan students, the Hungarian and so on, better than other countries. Why other countries? Because in Italy in this moment we have no students. no PhD students. We have money, but not the human resources. This is national security. So please, we want you to join us. I'm trying to recruit people. Anyway, we have a lot of projects, but not human.
Doctorat in Italia.
Our laboratory in short, we are working with National Institute of Standard Technology. You know, the TESA is the electrical gun that the American police use. The calibration system is made by our laboratory. It's about $1 million of contract that we have with them. But we need people for this. Again, we are working with our Minister of Defense in information communication branch, in particular for the detection of the radio signals. It's about $500,000 euro of a project. And with the Italian government, but always the military approach with the new share, including sensors, to detect the health of the people on the field. Is about 900,000 euros. Look, but also in this case, we have no people. About our activity on drones, we have a laboratory. This is the home page of the laboratory. Please visit and you may see our activity in this field. In particular about NATO. I suggest to visit this page. Here is reported all the information concerning the NATO Science for Peace and the Security Program. There are a lot of opportunities to catch, not only this type of activity like the advanced training course. And I will show someone. We started to work in this field with the Technical University of Sofia in 2021, so some years ago, with our first meeting with paid support of the NATO. Then we are involved in some workshops that are very useful to be inside the system. My suggestion is to contact your local national office and to try to understand in what workshop, in what research group you may go in. It's very important to begin to create a network of contact. For example, we were involved in this NATO APT 355, and we submitted and they accepted the procedure for testing drones. Okay, it's a begin, step by step to go in the system. These contacts are public and you may find all the information on the NATO website. After that, thanks to other people and other friends that are also in this room, were involved in some advanced training course. One was in Kharkiv 4 years ago. Another was in Morocco 3 years ago. And now we are here in Chisinau. But this is not the only activity. We are involved in a multi-year project. Is a project about 350,000 euros. It's a small research project. If you are involved in something, next step is submit a proposal for a research project. And they support this research project together, including some countries that are not NATO members. For example, Moldova is an excellent candidate for this type of project. In particular, we submitted a proposal for we call the ICE, inspection, maintenance, security, pushed by innovative robots, enhanced data communication and infrastructure digital twins. To look, the central position is Morocco, where previously we organized an advanced training course like this. So a step by step to go inside the system. And there are partners from the other project, for example, from Poland, Chisinau, and Italy. In this project, we will monitor, I don't know, infrastructure like harbor or something that could be critical infrastructure for Morocco. Okay. So a possible next step would be something like this, but for moment. Of course, from the research point of view, you have to propose something that is a state of art. In particular, here we are trying to realize a digital twin of spatial infrastructure. This project, this advanced training course, is practically son of another big project. I know that Tatiana Mulimaga will speak on this, so I would only to mention that our cooperation in Moldova is very, very long, about 10 years. And education for drone gives us the possibility to establish here a laboratory for drones with the course with the educational material and so on. Tatiana will speak about this in the next days. The list of the partners involved, the European partners, the 11 partners, 5 of them were from Moldova. 17 associate partners, a big project, and these are the results, in particular here in Moldova. Another opportunity for cooperation. Every year we organize a conference. It's called the Metro Aerospace. It's supported by Italian Army, in particular Italian Air Force. This year the conference will be in Pisa. It's just at the end of June. Some of the partners that I mentioned previously are involved in this conference, organizing some special session, for example, drones. So if you want to submit papers or to want to be in the loop, please contact us because this is a good opportunity. The conference is an IEEE conference, so the proceedings will be included in the IEEE Explorer that are indexed on Scopus and Web of Science. In the conference, there is always a session on military application for drones, and the Italian Air Force every year support us with some demo. This, for example, is a Predator that our Air Force uses. Next, what about the drones? So this is the main aim of the speech. Look, for a lot of people, drones as a toy or something to take photo in the movie during the wedding ceremony. For others, is something for military mission. But for me, is a mobile platform for taking measurements. Is an instrument. This is my view. Why? First of all, please note that there are several things. There is the aircraft, autonomous aircraft, remotely piloted aircraft system. All of them are, each of these terms is a specific term. And practically, we are speaking about something that can fly autonomously and controlled by a remote station. This for us a drone. There is now some official definition, starting from European Aviation Safety Agency, EASA, that as an official definition of drones. An unmanned aircraft system comprises individual system elements consisting of an unmanned aircraft, the control section, and any other system elements necessary to enable flight. So it's a complex system. It's not only the object that is a flight. In particular, for our application, we use this type of drones with a weight less than 4 kilos. There is a parameter that is important, is the MTOM, the maximum takeoff mass. It means that this parameter is proportional to the expected kinetic energy impacted at impact. So pay attention, you receive the drone on your back, on your head. So we will discuss about this type of drones, not big one, but something that we may use in our laboratory. You know, what are the main parts of this drone? Of course, there is the frame, the brushless motors, flight controller antenna, batteries, fundamental, payload, GPS and inertial navigation system, propellers, and the electronic speed controllers. These are basic components. The general architecture of the electronics of the drones. The single board computer, radio, sensors for vision, sensors for navigation. We will pay attention to these two parts. About the software, there is a software running on the drone and a software running on the ground control station. So if you are a software developer, pay attention to these two parts and the constraint, the limitation that you have on the drone and on the base station. How a drone like this may fly? You may have a vertical motion. You may go down by changing the speed of the propellers. You may go right and left, always changing the speed. And of course, you may have a rotation, Joe. All is made by changing, controlling these four propellers, four motors and then the propellers. So for us, drones may fly because they are doing measurements. And the drones for us are mobile measurement platform, making measurements for the mission. So measurements is fundamental for flying the drones and for the aim of the drones. Okay. Without measurement, there is no fly, no autonomous flight. Because on airplane, at least there is a pilot. Here, there is nobody. So it's important to understand measurement for drone and drone for measurements. It means drones require measurements for flying, sensors and measurements. The drone may be considered as a mobile measurement instrument. Look, according to our idea, this is a mobile instrument, but it's not flying. Okay, so for us, the drone is the next step of this piloting. There is a measurement instrument on the table, then there is this mobile measurement instrument, and then there is the drone. It's a flying mobile platform for measurement. So there is a strict link between drones and the measurement field. I'm sorry, but I'm a professor of measurement, as you may understand. So about the measurement for drones, you need the measurement for navigation, measurement for security on drones, and measurement for drone traffic. And then by using a drone, you may collect measurements, environment, and so on. About the measurement used by drone for flying, it means to collect information about altitude, position. You need this type of sensors. Inertial measurement unit, ultrasonic sensors, attitude LIDAR, camera, GNSS, RTK systems for communication. So you may read here for each sensor what type of measurement you may receive and what type of problem you have in this specific measure. A problem is in the navigation. In the future, you have a lot, probably Bartosz will speak about this. In the future, we have a lot of drones flying anywhere. It's like a traffic. What are the rules? If your drone must go in a line, what is its position? What is the uncertainty in the position? Because these are autonomous flying objects. You may crash, have a crash in the air. So how to measure the uncertainty in this case? This will be one of the next big problems. So navigation and the measurement for drone navigation is a big issue. We need a lot of information, but accurate information. So we have to test how to test this future flying machine, autonomous flying machine, is another problem. And the position rotation using information, of course, to localize the measurement provided by the drone. An example, look, this is a piece of electronic, an accelerometer, on laboratory, laboratory. You may see static condition, there is no problem. If the same component is on the drone with the propellers running, this is the spectrum. The loss of information. So you need some damping platform in order to isolate this electronic with the sensors from the flying platform, in order to receive something like this, the same component, static on the table, flying with some solution. So in order to have this result, you need to collect all this information, but also fundamental to collect in real time, hard real time online, by using battery, but using low power, or your autonomy will be reduced a lot. So it's a big challenge from a technological point of view, not only for people that are expert in flying something, but also for people in computer science, in electronics. It's a mix of science. Also for people working in power electronic, how to reduce the power that the drone is using, not only for flying, but for computing. Because these are image, is a lot of power that the processor will absorb. So it's a very big challenge, in particular for these small drones. And if you know that the last version of drones are trying to include commercial drones, solution to increase the performance in terms of autonomy, resolution, and so on. So now we may see the other aspect, drones that fly for measuring. Of course, there are satellites to do this, but satellite is very far, low resolution, high cost. Often there are clouds, weather change. You have not the possibility to have in real time something on the field. We are looking at TV and some movie from Ukraine war. You understand that. With drone, you may soon be informed. So this system may provide anytime, anywhere, soon information. And for what type of application? Practically all the applications. This is only fantasy. Yesterday, I had the possibility to note the application in the pandemic time. It's new for me. Thank you for this information. So, something medical application. Okay. So there are, for example, what are the positive aspects? This object is low light, small size, low cost, easy handling. Is a platform that may survive, I don't know, close to vulkan, where there is not in the environment. It's a very flexible platform. But there are a lot of limitations. No long autonomy, payload is relatively low. There are some uncertain sources when you want to do measure, actually measure. For example, it's very common to use the drone for photovoltaic system monitoring to see if there are some cells that are not in good condition. A photovoltaic system is a very, very large area, and this is the way to monitor soon at low cost. It is used in Italy a lot from this point of view. These are the steps that you will carry out in order to identify if SL is out of order. The same is the power line inspection. Is another common use, and you may identify with a thermal camera if there are some losses on the line, or if one of these cable has some mechanical problem. There is no risk, no problem in carrying out this type of measure. Also in this case, these are the steps to perform, and the problem you may have is the cycle automation. Structural health monitoring, use the video camera. In this case, often the camera is not down, but is up the drone to see the roof. For example, in the church, if you have a dome in a church, you want to understand the state of a dome. The camera in this case is up, not down. A specific drone only for this type of monitoring. And also in this case, there are the steps to perform and problems to make. Precision agriculture is very important. I think this could be a field of investigation here in Moldova. How to use drone for the agriculture. Moldova is practically flat, so it's the best approach to see if the vegetation is growing in a uniform way, if water is spread uniform in the field, if there are some illness for some specific plants. This is a typical application in a territory like this. Of course, you may see, for example, with a specific camera, what is, for example, the concentration chlorophyll anywhere, the color of the vegetation, and so on. One of the two PhD students coming from Iran, is a lady, is just working in this field to move with this technology there. Okay. Of course, then next step is the environmental monitoring. To watch the state of the environment, the temperature, humidity, and so on, the state of the sea, for example. There is a speech from Professor Mindikowski from Poland next days, and he will inform you about not only the state of art of this type of drone, but also drone in the sea, under the sea. They are from Gdynia Maritime University.
Actually, today they.
So another thing that for us Italians is very, very important, drones for archaeological investigation. Before to escape, and now the way is to investigate the area with a drone, with some specific camera, and to understand if under the land there are some change, if there are walls, objects, metallic objects, and so on. And also to realize maps of this zone. From this point of view, there are two fields to investigate, the aerial photogrammetry and aerial laser scanning. This is a dual-use technology, so it will be used for the archaeological investigation and for other type of investigation. And this is an example of aerial photogrammetry. It is important in this case to evaluate the uncertainty of the measurements. Because often you may reconstruct walls, other objects, but what are the sizes of these objects? So how to design a drone to be considered as an instrument? For example, in Italy, we are discussing now about the drone to be used after a crash between cars. Often in Italy, as I think in Moldova, the police arrive by car and take the measurements between the cars and the building. I don't know, if there is a man on the road, where is the photos? It takes a lot of time. We are thinking a police car, and on the roof of the car there is a drone. It automatically may take a photo, movie, measurements of this situation. This could save time and to be more objective from measurement point of view. What is the legal problem? What is the answer time? If there is a policeman measuring with an instrument, the uncertainty is declared by the instrument and the expertise of the policeman. But in this case, we have to certify from a legal point of view this type of measurement. Until now, there is nothing. How to guarantee the traceability of the measurement chain from the primary standard to this final instrument? There is no solution until now. So if you consider the drone like an instrument, you need a calibration certificate. There is no solution now. Okay. If you know something about electronics, you know that this is the block scheme of electronic instrument. Very easy. Sensor, amplifier, analog digital converter, and digital elaboration. And more or less, you know what are the uncertainty sources, means the influence of the sensor on the electronic amplification and on the converters. It's well-known information. But what happens when you consider the drone as an instrument? Look, in this case, the drone is a more complex instrument because it includes the previous blocks, more other blocks, and of course, more other uncertainty sources. So you have to take into account the weight, the power consumption, communication link, the measurement certainty. All of these will give you the final performance of the drone. The selection of the onboard sensors, the calibration method for each part of this drone. So this is a new instrument. It's a flying instrument. There is the common, the classic scheme, but we have to add this part. But what is important, you have to add also the new uncertain sources. For example, the magnet of the motors, they create noise, the electrical noise to the boards, to the sensors. That in this scheme there are the vibration, the mechanical vibration of this mobile platform is another noise source. So this is a new scheme of an instrument drone based. but it's fundamental to take measure. And if you want to have a traceability of your result, or you are taking only picture for wedding ceremony. So you may see the complex system that now you have to manage from the measuring point of view. There is also a chain of steps to do in order to arrive to the uncertainty of the result of this experiment. What are now the trends in this specific field? Trends come from these. Look, this trend. It's clear that drones will be part of our life in future, but not only flying, also autonomous. I'm speaking in general on the autonomous systems. Also the new, the cars with autonomous driving system practically are included in this development. A Tesla, a car may more or less move without a pilot. So there is an explosion of this technology in any field of human application. So what are the main requirements? The autonomous navigation, fundamental. A group of drones flying together, not one, but thousand and thousand, all together. And new sensors to guarantee on this specific system accuracy. Think about this scenario where a lot of drones will fly to move with delivery object information, take picture. We need a system to control all. I think that Bartosz should speak about this more or less. We need to know the uncertainty of each path to avoid collision. And we have different drones from different producers, but they must share the same rules. So there is also a big legal problems. Another thing, the swarm of drones. This is the Guinness World Record. Look, more than 3,000 of drones flying together. Probably you already know about this movie. This is an example for Pacific application, but maybe think if 3,000 drones will arrive together, what could happen? This is a great opportunity, but it's a great problem. It depends on dual use technology. They could arrive from different paths, but arrive in the same place. Okay. So sensors, another challenge, sensors that during the mission avoid to create panic problems, injury, and so on. And we have to test the interaction between, I will show a movie later, on the drone and humans. What happens? If there is a crash between two cars, more or less we know. But what happened between a crash from a human and a drone? So we have to speak about security and safety from drones. So about safety is important. What is my time?
No,
I can continue for hours.
yes, yes, please, 50 minutes only, only 50 minutes, only 50 minutes from the top.
So about the regulation, the European regulation introduces some definitions important for us. Accident and serious incident, and then so there are three definitions. This is the first, the second, 10 minutes, and the third definition to understand the gravity of the event. There are a lot of now of these events because we are using a lot of drones. So pay attention from this point of view. There is a document on this published from this European institution. And of course, you have to pay attention to all phases of the drone flying. And the possible causes to create this unpleasant situation. So, some solution to increase the drone safety. First of all, to put on board other sensors, but this reduces the autonomy because the weight will increase, battery will absorb, you will absorb more energy from battery. And more test procedures before the flight. This is an overview of all the action that you may use now. For example, it's very easy to see some protection around the propellers in order to save the operators from this type of injuries. But there are some studies to use soft propellers. Is another type of activity. So new materials will be used as propellers to reduce the impact between humans and drones, or to use some special optical system to stop the propellers in case there is a contact. I don't know if you destroyed a propellers. It is enough to take away 1 millimeter of propellers and the drone lost complete stability. In my first test, I destroyed one of these propellers and the drone is completely out of the control. It's not stable. So it's important to have flying testing. But there are some proposed solutions how to test on the field a drone, how to monitor and to test a drone flying, but nothing is standardized. For example, this is an example of a propeller with a missing part. There are vibration, a lot of noise, instability. Of course, this is very important to avoid collision for autonomous flying. If you have a fleet of drones. And you may see that in this case is very important to study the sensor fusion. You have some sensors on board, and to use the information of a lot of sensors to better understand how to control the drone. For example, here there is instability, and this drone is fixed. So new algorithms for the sensor fusion data. A list of sensor active and passive to be used in this case. This, for example, is a result. A real-time algorithm is able to avoid obstacles. All is in real time. Okay, so from testing point of view, there are a lot of tests on the battery, on the propeller, on the motors. What is the state of art? If you have a car, now you know there is a procedure how to test the car. If we buy a car, we know that this car is produced and tested, certified according to some procedure, standards. If I produce a car in Hungary or Moldova, in Italy, the standard is the same. But what happened for drones? Nothing. Now there is ISO CD 4358 is a test method for similar multi-rotor unmanned aircraft system, but is under development. You may find it on the web page. If you have to pay if you want to download, but the abstract and general information are included. But the main problem is that you are trying, what are the trend? To certify, I don't know, the motors, the propellers, parts of the drones. Also using with the tunnel and other facility from aeronautical tradition. But there is no, until now, a system to test all the drones. And more or less in flying condition. We realized with an Italian company a test bench called the drones bench. Is a metallic structure with some load cells. You may link the drone to this metallic infrastructure and to give the drone the possibility to fly, but is linked with some chains, a metallic structure. From this apparatus, we realized for NATO a procedure to test drones. So think all is connected. At the end is the procedure, but it's not important now to see it. We realized a procedure were included in this NATO document, introducing some parameters that define the global performance of drone. If you may read the papers about this, public papers. Last but not least, the safety on the ground. What happens if a drone visits your body? So if you meet a drone, how to quantify the collision between you and the drone? For example, there are some experiments, a drone and a window, a glass window. there are a very important test. I will show this movie. They are using the technology that they use in the American, I don't know, American sport, when they produce helmet. The same technology they are using to try to happen if there is a collision between a man and a drone. They are destroying drones.
Yes.
And also to understand how to change the shape of a drone to reduce the engine.
Cristina, presentare sala,
In the big one.
sala de conferință 119, locul la drept. Vă rog, terminăm.
What is important that all these events are not standardized. There is not a clear idea until now. All is at the research state of art. Okay, last is drone security. We can open here another, I don't know, 2 hours of discussion. Pay attention because now, as you know, drone is used not only for Pacific aim, but also for non-Pacific aim. How to detect drones? For example, in Italy, we have a special inter-army center, as in Sabaudia, close to Rome, for the development of technology to stop drones. It means to detect and block drones. I suggest you, if you want to read something very interesting, there is a paper written by South Korea colleagues. Is a wonderful paper on all the action that you, until now, you may carry out to identify and block, stop a drone. And there is, I would say, the flying object identification, the drone classification, the drone identification final, and of course, neutralization. You see, there are specific sensors. So there is not one solution. This is a problem. It's a big problem. But you need a collection of technology to work together. Only in this way you may identify, to know where is, what is, and then to stop or not. This is a big problem because all this technology must work together and in real time. So you have here a list of the sensors to be used, and then after the detection, the possibility that you have for jamming or, I don't know, shutdown to try to neutralize the drone. So, my conclusion, here there are some possible points for discussion in which we are working. And if you wish, there are some videos, tutorials that we produced for IEEE. And we offer in our PhD course, we have a specific for our PhD student, a specific course for measurement for drones. I don't know, it's 4 or 6 credits that we offer. And this is a list of papers in the field. Okay. This is just a part of our team with the Italian modern art, close to our logo. Thank you. I'm sorry if I was long, but
Thank you. Please, questions, suggestions, proposals. Please, Professor Vyacheslav Pierzho.
You, Professor, for the first, thank you very much. You also for this presentation, which show us all the aspects of new technologies, drones, measurements, and what is your opinion? What would be best way for data processing? So on-board data processing or on-ground data processing for the data used by drone. What is your opinion here?
Look, it depends on the application. Of course, if you are application, if you are in Ukraine, I'm sorry, and you have to see something soon, is fundamental probably to have more application rules. But so is a different approach. If you want to elaborate image of a church or I don't know, a power line where there is no real-time approach, you may collect this image and then to process. It is a borderline, I'll say, there is no a specific approach. It depends on what you wish. And first of all, on the money that you want to invest. If you are buying a Chinese equipment for a first test, you may collect photos, movie, and then to elaborate. If you the real-time approach, of course, all is to be adapted. So I'm sorry to underline this. All in this field is related to the application and the money that you want to invest.
So all will depend from the tasks which have to be realized the drone. Yeah? So will be full autonomy system or only the system which will send the information to ground computer and to process to analyze this one.
For example, I spoke about the example of the police car. I'm sorry if there are policemen here, but people consider that they are stupid men. So the application is to realize a system that is as autonomous as possible. In order to avoid that there is a human interaction in this measurement process. In this case, you need an algorithm that take photo, movie, may measure something with maximum autonomy, with no interaction. Probably the chief of these policemen in the remote station may receive the result. This is a case in which the autonomous system probably is at the maximum level. And of course, you have to pay for this.
And another aspect, another question about the certificate of calibration. Okay? So if we will use a standard camera, which was certificate, so I suppose that here we will also some problems in calibration.
Look, if you use something that is a certificate, but you use these on a drone, it's different. Because this certification was done for not flying, the problem. But when this apparatus is close to interference produced by motors, for example, what happens? From a vibration. So we have to test and certify all the machine, all the drones, not only the sensors, the single sensor on board. I show you with a photo, a sensor that is certified. On a table, you have a result. On the drone, you have a different result.
But what about the using of the camera on the satellites? not nano-satellites, micro-satellites, it's the same camera.
But you have no certification for legal application. This is a problem. If you want to have legal application, for example, to avoid the use of policemen, for example, you need a certificate. But you have to certificate because in the it's metrology, the approach. There is a standard, there is a reference chain, and at the end there is the instrument. In this case, the instrument is flying. How to certificate it? Don't know. You know, issue.
Thank you very much.
For example, in Italy, is another example is very in particular, I'm sorry, in the south of Italy, to build in a legal way a building. And the police now are trying to monitor this situation. But often in the court judge, they may say, my palace, my house was 3 meters far from the road, some living. Another one, no, it's not 3 meters, 2.5, but I use a drone. But is this drone certified? No. So there is no legal basis. This is a problem. The law, of course, the rule is not a problem, it's an opportunity. How to introduce this new measurement instrument in a legal base? This is important. Also for injury. If you buy a car, you know the class of a car and the protection of the car. No? There is a specific scale. If you buy a Mercedes, you know that probably is at the top. If you buy another car, probably you know that first of all you could die. The same for drone, but there is no legal approach. So now it's not a technological problem. It's how to introduce these apparatus in our civil life with the rule that we have to be considered like a car, like a motorbike, and something like this. Okay.
Thank you very much.
Okay, thank you very much. Now we have a coffee time for 45 minutes till 11 a.m. So at 11 we start the next presentation. Deci la orele 11 după pauză de cafea, vă rog începem următoarea prezentare. Revenim toți în sală aici, vă rog frumos. Mulțumim. Și coffee time. Dar nu mă sunt așa rău ca el.
Am uitat eu. N-ai uitat nică, de normal. Eu am дати мікрофон порнути.
Yeah, colleagues, now we have the next presentation. So our next speaker is already online. And first of all, I'm sorry for this short delay because we had some interview here. Both Professor Daponte and me. And another side of our event is also to promote our science for peace. That's why we try to be open as much as possible. So I'm very sorry for this delay. We should start the next presentation. I would like to ask Associate Professor Martin Hromada from Faculty of Applied Informatics, Department of Security Engineering, Czech Republic, Tomáš Bata University in Zlín, to speak about new methods and approaches to increasing resilience of critical infrastructure. Dear Professor Hromada, do you hear us?
I hope so, that you also hear me.
Can you speak?
Yes, I'm trying to speak. I hear you. Do you hear me?
Ну, ви вибір. А паразит, значить.
Do you hear me, please?
Let's wait.
Я сканував.
Маузі?
Сканував. Ну, ловозим піде.
Як маудіс?
Ну, я ловозим. Я лончарк свой.
Do you hear me?
Це лек.
Російський месаж.
Do you hear me? Hi, everybody. I hear you, but maybe you do not hear me.
Ну, я так вот держав вибір, що не ловозим.
Do you hear me, please? I hear you, but maybe you don't hear me.
Ні, це
I'm
ж
trying to
наша
talk with you.
Я бояла воводі.
Yes, but we don't hear you.
But I think that my microphone,
To the box, потом.
I think that my microphone works. I don't know if there is some technical problems on your side. Do you hear me?
Алло.
Do you hear me? Do you hear me? Do you hear me?
Окей, микрофон lucrează, deci el noi din cauza noastră nu se aude, este вообще.
Hi, do you hear me?
Okay, just a moment, please, Vic. Okay, can you speak now?
Do you hear me? I'm still trying to speak with you.
So no sound from your side.
I'm so sorry, but
Yes, I think so. This
Do you hear me? Do you hear me?
1, 2, 3.
Still don't have any reaction from your side. Do you hear me? Do you hear me? Am I the first presenter online today? Do you hear me? Do you hear me?
Nu, e Женя plecă. Păi spune cum se aude microfon. Difuzorul să. Așa.
Still trying to talk? Do you hear me? I think that everything goes perfect.
Spune cum se aude difuzorul sau care că așa.
Do you hear me? I'm still trying to talk.
Știi. Женя, ce-ai făcut tu că orice nu aud eu și vorbește oamenii pe online? Mă auzi? Membrii încearcă să vorbească de online, să prezinte ceva și noi nu-i auzim deloc. Asta cum? Microfonul inclus la dâns. Dar noi nu se aude în difuzor.
Do you hear me?
Nu, că e că... Uite că vezi că eu de la mine pornesc și nu se aude deloc, practic.
Do you hear me?
E problema în sunet. Da. Da, afară nu se aude. Anume boxa asta de la Logitech, cum e trebuie de setat?
Do you hear
Și am
me?
dat la maxim.
Do you hear me?
Cum e conectat?
Do you hear me?
Ah,
Do you hear me? Do you hear me?
mhm.
Do you hear me?
Yes, please try to speak now.
Do you hear me, please? I'm surprised to see you. I'm surprised. Not to say. Do you hear me? Do you hear me? Do you hear me?
Yes.
Do you hear me? Do you hear me? Do you hear me? Do you hear me? Do you hear me?
Da, să dici. Ce faci? YouTube
I'm still trying. Do you hear me? I'm still trying to talk. Do you hear me? Do you hear me? I'm still trying to talk. Do you hear me?
Da, încerc să fac conexiunea cu... Domnul, nimic страшно, te închide. Stop, dacă era... Hai. Microfon, vorbești ceva tu. Cu microfonul tău. 1, 2, 3. Bună ziua! Înseamnă că la noi totul e normal. La dânsul cu microfonul Nu, ceva tău. Department of Safety.
Domnul Palade, noi vă auzim perfect.
I don't hear anything.
Because we check the speaker in our conference room, and everything works properly. Please try again to speak with us.
I'm still trying. I'm still trying. I'm still trying.
Can you change your microphone? Martin, can you change your microphone? A different one. Thank you. You wait, take your time.
Do you hear me now?
Yes, now we can hear you. Thank you for changing your microphone because my colleague checked everything here and it's working our conference room.
Okay,
Please.
so
Okay, now
fine.
I'm here. Thank you.
Yeah, perfect. So, okay, I'm trying to going to be very brief and very straight. Firstly, I'm
Sorry, the sound is not good.
okay, but I try to improve it. Just give me a few seconds. Do you hear me better? Do you hear me better? Do you hear me better?
No.
Do you hear me better?
No.
I'm still trying to talk. Do you hear me?
The sound is very low. The sound is very low.
I'm still to improve my another microphone. It's better to hear me.
No improvements.
Do you hear me better? It's better or not? Do you hear me? Do you hear me better? Do you hear me better? Do you hear me better? I'm still trying to improve it. Do you hear me better?
We can start the presentation from our computer here in the conference room because we have
Okay, I'm going to cancel the sharing my screen.
yes, and we start presentation from our screen. And let's try just the sound from your side.
Okay. And do you hear me clearly? Do you hear me clearly? Do you hear me? It's better or not? Do you hear me?
So from our yeah, but we still very bad sound.
Do you hear me?
Now it's better. It's not clear. It's not a clear sound. And so how about the internet connection? Maybe it's too slow to be enough have a good sound.
Yes, but I think it's on your side. Do you think I'm on the faculty, so.
Not sure that
Do you see our desktop screen now? Can you see our desktop?
Yeah, I see your desktop.
Now, my colleague will show you how to make your microphone settings to get a better sound. So please hold his action now.
Okay.
First, sounds. So you can see now the sound screen. Microphone.
Yeah. Maybe I'm able to show you my screen.
And the microphone boost. Please increase your microphone boost and microphone level, like it is shown on this screen, please.
I try to. But I think that we've got a different version of Windows.
That's it. There is another suggestion now. That you can use your phone for a sound, for better sound, and you can use your computer just to show the PPT presentation. If you join,
Do you hear me better?
via your phone, you can speak on your phone, and you can use your computer to present your slide without sound. So sound should be done in your phone, not by your computer. This would be a way to solve this issue. Starting your presentation on your computer, but speaking in English. Just want to ensure that when you conference by your phone to just speak.
Do you hear it better?
No, not better. It's not a clear sound. It's not.
I'm still trying to improve it. Previously, I didn't have any problems with the sound.
Como este, Antônio, uma ação e pode solicitar, não apresentar, pode solicitar apresentar, acho que esse elemento fácil. Eu já estive com isso. Se o problema vai lá no é o problema. Nessa velocidade. O tempo.
It's better.
Yeah, it's better, but not clear. Not clear sound.
As I mentioned, I try to improve it, but
So now it's good. Now it's good. But please try to speak a little bit slow.
okay, it's better when I'm speaking slowly. May I start the presentation?
Yes, please. Please. Now,
Okay,
I speak over your phone.
Okay, I try to speak slowly and go through my presentation.
Please. Okay. Thank you.
Okay, so I'm so sorry about these problems, but I try to be very brief due to the fact that I'm going to have an important meeting. I'm from Thomas Bata University, from Czech Republic, and our research activities are mostly related to critical infrastructure protection and resilience. So it means that my presentation will be about the methods and approaches that were developed by our research teams in Czech Republic. Firstly, I will describe some aims of our previous project related to assessing resilience or talking about the resilience aspects in wider context, where the wider context is seen through cascading impact assessment, qualitative evaluation of synergistic effects, complex approach to assessing resilience, and resilience assessment in electricity critical infrastructure from the point of converged security. So the aim of the project was a research in critical infrastructure resilience issues, mostly related to dynamic linkages and interconnection assessment with emphasis to European sectors, European important sectors. I don't think so that it's not necessary to talk in more detail about the aims of the project, because I think that you are able to see it and read it from my presentation. So I'm trying to go to the outcomes. Okay, the first aim or the first topic that we need to solve is to define what does it mean if we are talking about the cascading impact assessment. So this is just a very brief philosophy description of aspects that create the nature of impacts on a critical infrastructure system. You need to know that these pictures and all findings that I'm presenting, you will find in the articles that are part of my presentation. So this is the short description of the ways of activities or spreads of impacts in the system of critical infrastructure, where we've got a direct impact, cascading impact, and a synergistic impact. So it's not only about the cascading effects, but also synergy effects that are much more complex and may occur higher disruption of the critical infrastructure system from the state point of view. This is just a very short background how to evaluate or how to assess the cascading impact. We see it from the perspective of process management, methodology, evaluation criteria, input data, and so on. Very important step is the definition or calculation of passivity and activity coefficients, where the activity coefficients show us how many subsectors or sectors may be affected by first sector or the beginning sector disturbance or destruction, where also the passivity coefficient show us how many subsectors may affect my sector or the first sector. So these two main coefficients give us the feedback of the criticality of the sector in context of their interconnection to other subsectors. As I mentioned, another challenge for us is not to see the critical infrastructure from the perspective of cascading effect, but also from the effect of synergistic effects. It means that we are go to second or third step of reading the impact of previous critical infrastructure disturbance. So we are able, by calculating the transfer coefficient, to say uh, the degree or the level of potential impact through linkage to another subsector. So we use for this purpose Levontjev's economical input-output model, where it shows us the possibilities how to evaluate or how to define the level of potential impact of first sector disturbance or destruction. This picture shows you the example when we've got functionality reduction of electricity in level of 10%, and the first, second, and the third level of synergistic effect. You see that maybe after 72 hours, the critical infrastructure system in Czech Republic will should have a very big problem. Another very important topic that we solved in our previous activities are resilience assessment. You are able to find this article or this approach in the article in International Journal of Critical Infrastructure Protection, where this article is one of the most cited and downloaded articles. So I hope so that someone see the outcome of this approach. This is just a very brief and short description of the process, how to use the Sierra methodology. We call it Sierra, but it's critical infrastructure element resilience assessment, where we are working with this diagram, with the philosophy of each aspect of the resilience, and so on. This is just an algorithm that defines the process, that defines the steps, how to assess the resiliency. So please do not hesitate to look on our article, and this is just an outcome of the resilience assessment, where we see it from the perspective of three main attributes: adaptability, robustness, and recoverability. This is just a very brief and short example of the tables that we use to evaluate the above-mentioned attributes. This is just an example assessment of the elements of robustness with respect to cyber attacks. This is the recoverability aspect example, and this is the adaptability aspect, and so on. Another step another activity is related to convergence of security measures, because sometimes when we are trying to apply some relevant measures in physical protection or physical security, cyber security, we did it separately. But we need to make a convergence of these activities or measures, because when you've got problem with your access control, it also affects the level of the cyber security. So this is why we are see it from convergent security and put together mostly three most important security aspect: physical, cyber, and operational. So another article will show you how to use this philosophy in context of a real critical infrastructure element in Czech Republic, mostly in connection with electricity sector, where the innovation in this process is the definition of penalty factors. In the beginning, we see the resilience level, for example, in the scale from 0 to 100, 100, and each penalty factor just decrease the resilience value. So please see the article and you will find the philosophy and its application in the practice. So this may be one of the last picture show us what happens if there is a problem with some security measure. One security measure may impact another security measure, and you will see the decreasing of resilience level, and it's increasing when you apply another measures in solving the impact of any event it may occurs. I'm so sorry that I'm so short and so brief. We are very limited, and as I mentioned in the chat, that unfortunately I've got a very important meeting. But I think that there will be a place and possibility to contact me in by my mail address. And if there are any additional questions, I will be very ready and very happy to answer to it. So thank you for your attention, and I'm really sorry for the problems that occurs. So are there any questions? I do not hear you. Do you hear me? Yes, I hear you now.
So we have no question, and we thank you for your presentation. And I would like to ask you to email me your presentation so I can share it with all our colleagues.
I already sent it yesterday. So
Oh, okay, I will check. I have a lot of emails. I will check. Sorry.
okay.
Okay, can I share with all of our attendees and speakers?
Yeah, you will be very welcome for it.
Okay, thank you. Thank you. Thank
I
you very
also
much.
thank you. See you soon. Bye. Have a nice day.
Thank you, you too. So next presentation is out of event automatic UAV system as an enhancement for critical infrastructure protection partners. Let me stop preparing the invention. No, just leave it. Leave it like that. Like the Microsoft Teams application. It's take your time to fill the facts. Yeah, just have plenty of time. I will keep you long for the lunch for sure. Just starting the Microsoft Teams.
Okay. The application is open, okay, so I will share my screen now. People microphone. I have the same. Okay. Screen is on. All the people in the online conference. Check. So, I will present you. It is that there is some. Chisinau. Also, but it's double some, down, some, down. Sound from that from. Open for the name. Ladies and gentlemen, today I will present you the outpayment system. It's automatic UAV system for design in our company, JSW Innovacja. I will start the presentation with introduction of our company and our team. It's a short movie. I hope the sound will be correct, but we will see how it works. If not, there's also the subtitles that I will also describe the company. The JSW group is the company that excavates the coal, coking coal. So the coal that is needed to produce steel. And our company is one of the daughter companies responsible for the R&D in the project. I think that the sound is not here because you just disabled my sound. Okay, so that's what I suppose that will happen. And my team in our department of R&D in JSW, we are not
experts that can design also all the mechatronics components, starting from the mechanics of all the UAV, of all the avionics in it. We have the possibility, the tools for fast prototyping, and we can 3D print all the components that we design. We can we have the CNC milling machine just to design the just to produce the design elements, and so we can just create the electronic circuits. In the virtual reality, we know how to move the real objects into virtual world. There's the possibility just to move the real tool to the virtual environment and operate this tool in the virtual environment with the VR gloves. That's the very nice feature that we are capable of now. And that's basically the area of our expertise. In the autonomous part of our department, we are having now the projects only focusing on autonomous aerial vehicles. We tried to create one also for riding on the stacks of coal, just to test the quality of the coal, but the project didn't start yet. The auto events that will be presented here for you as the proposition for critical infrastructure protection and monitoring was designed and developed during the project co-financed by European Union, and it was designed for automatic spatial data acquisition and analysis that will automate the inventory, modeling and volume calculation for the mineral resources. That's what Professor Da Ponte like earlier today said, that the drone is just the platform for the different kind of measurements. So now we have the platform, we have the automatic system that you will probably, I hope you will see today, because depending on the weather conditions, I hope we will be able to start. And I'll show you how this system works. So the automation, the platform is fully automatic. It can be remotely controlled, or you control it from here. And we changed the measurements unit that was designed during the components project into the very simple observation net, just to present the possibility of the system. So moving to the system, our auto invent system is during the project we had to check, and the R&D in that project was focused on checking the possibility to improve the quality of positioning using the robotic total station commonly used in geodesy. We put it the prism over the drone, and we were just not controlling but tracking the drone and using that position to improve the quality of the positioning during the flight. The outcome of the research was that it is a good way to track the drone, but only on short distances, because when the drone was further around 1 kilometer, the tracking was lost. So now we are moving this result, and we are using this result to increase precision in landing system and automate the landing procedures using the robotic total station. The other part of the R&D in the project was the measurement unit. We wanted to increase the precision of all measurements using dual sensor and having fusion of that data So the data from the full frame camera as the photogrammetric, doing the photogrammetric that, and also scanning the area with LiDAR and getting the point cloud from LiDAR. So with fusion of that data, we improve the precision of all measurements. And so the measurement results were the point cloud, also with put it on the textures from the pictures, and we will able to model the stacks, and we are able to with the digital elevation model calculate the slopes of the stacks. Here you can see just the some of the results that were obtained using our system. And we used then the data after frequent flights, because the idea of the measurements is that you can do the same flight, do the same measurements frequently on the daily basis, weekly basis. Here you can see the differences in two measurements that were made week by week. And so that was the idea of the whole system, the R&D included in the project, and the idea of automation of the calculation process. Within the system, we have created the platform, the drone that can fly approximately up to 30 minutes. The payload that we can have, so changing the measurement unit that we had in the project for any kind of observation unit or any kind of different set of sensors, we can lift up to 6 kilograms. And the positioning accuracy of the drone is below 5 centimeters now, and so we can track the drone using the real-time kinematic system on the global navigation system improved quality. And it's the drone for the drone we have in the project allows us to keep the drone in a safety conditions between flights. The aerial drone is supposed to be used for charging the batteries in the drone between flights. It was supposed in the project to download the data. That's why the title of the project was quasi real-time modeling, because all the modeling was done after the drone landed, because we didn't want to transfer all the data in the real time during the flight. That was the idea. We didn't needed that in the real time for these purposes. Now for the monitoring, the real time transfer is required. That's why we have added the communication model, and we will see that I can have the real time data during the flight, send it to me through using the internet, even here to Moldova. And the other very important part of the flight is, as Professor already pointed, is the safety. We have the weather station and monitoring. You can see the monitoring of flight conditions of the surrounding area of the landing spot. And also it is required for us in Poland just to coordinate the flights of the UAVs with the manned aviation, so that there will be no collisions in there. And so we have the special software for that, that allows us to inform the Polish aviation agency that we are starting the flight, that we are doing some operations in a specified area. And the weather conditions that does not allow us for the moment to fly is the rain. It is raining now in Poland. That's why we have tried to fly between those gaps. That's why I was just before my presentation, I was excited to check if we can start from here. So yeah, we have the flight successfully performed just seconds ago, and I hope there won't be any rain just right now, so we won't be able to start again. And also the winds cannot exceed 10 meters per second because the drone flies 10 meters per second. So the wind exceeding that will not allow him just to fly and stabilize the coral. And I think that will be enough for the introduction. I will just move to the live presentation. Here on the screen, you can see our ground control station interface. And in the middle, you can see the drone with the aerial drone. And the area that is circled here is the allowed distance to fly from the drone. It's 2.5 kilometers from the station. That's what we can do right now because of the regulations of the Polish regulations. So that's the distance you can fly with the drone. And on the right, you can see the monitoring from two cameras. One is outside the drone. The camera that shows you the aerial drone. Now it's put it on the trailer so that we can move it from one location to another and perform those flights. And the other one, the top one, is the camera that is put it inside the drone so that we can see what is going on with the drone itself. And the measuring unit, the measuring head that we have on it, it's not something very sophisticated. It's very simple camera because the idea to change from the automatic measurement system or the automatic monitoring system for infrastructure protection appeared because the Polish oil company that is transferring the oil around the Poland find out that such system will be very good for them to monitor pipes that are on the overground pipes that they can monitor that, they can easily and fast move to the location where something occurs on they've got some alarm on that. So that's why we just do the changes in the system to have the possibility to start the monitoring and just get them all the required features that they have. So we will start the preparing the flight. So I start with the setting the scheme, setting the mission. I'll fly from the dome just like 200 meters now to the left and back to the line a little bit further. And the idea of the flight and the requirements from that company was that it can fly, that the drone can fly in the mission on the route that was predefined by the operator on the specified locations. I just put the points on the line. It can hold the position, so it can monitor what's going on there if the operator just finds if something is going on there. So the mission is set now. I will generate the mission. Mission was generated. After that, I put the start mission. So that's the data of the mission is sent to the drone. After the confirmation, I get the command send confirmation, and the procedure is initiated. You can see on the left corner that there is a preparing for start mission. Now the landing site is being prepared. So the drone is just checking the weather conditions. The weather conditions, you can see here there is we just, as I told you, hard coded it so that it won't prevent us from something, just to show you. The dome just opens, so the drone will be moved now with the elevator up, and after going up, the drone will wait for the magnetometers to calibrate, because under the dome, all the electronic equipment down there just will not be able to give us the proper heading. So that the drone will wait for a few minutes, for a few seconds. It's not really a few minutes, but it's we just decreased the time as much as we could, just to have the enough quality measurement of the drone. So now we are waiting for drone. So now the drone is calibrating and sending. After that, it will send the information that everything is good and you can start. And that's the point that we need to wait for a minute. And the mission will be like that it will fly. When it will be coming back, I will just move it back to one of the points that were on the route. That's the idea. Now the drone is connected to the mission, and the mission is uploading to the drone. And after the mission will be uploaded, mission has uploaded, the drone is armed, is arming. We are waiting for the confirmation if the drone has armed. Now drone is armed and the propeller starts and the drone takes off. After the drone takes off, we can see the remaining flight time at the bottom bar. So we have like 90% of the time that the drone can fly available. So that the operator will know at some point that the drone will automatically stop the mission and return to the base. If this time will be not enough, then we have the procedure just to return home. You can see the drone moving on the map from one point to another. And with the slide view, the other tab, we can see the live stream from the drone. So we can monitor what's going on under the drone in the real time. We have the little lag here because on my screen it's a little bit more perfect, that we are just sending the same data through the internet here and back. So that's why we have a little bit more lags. So now the drone turns, so it's finished the first leg. We can go back to the monitor or to the control station. We see that the drone is moving the second leg. Now it will turn back. You can see that on the right screen that the dome for the time of the drone operation has closed. So it is not open and not absolute. The conditions are not affecting the drone. Now the drone reaches the endpoint of the mission, preset mission, and after it will be moving back, I will just hold the position. I will just move it back to one of the points before, so that we will see how it works, the holding position feature. So now the drone moves back. So I will just click on the last point and move the drone back to the last position right here. Command. So the drone should just move back. It got the information flying to the point, and the drone is flying back. You can see on the screen, and we can check on the live view that we can. It will the vision should stop at some moment when the drone reaches the final position, so we can just monitor the area that was predefined for the by the operator, just to monitor this area. For now, we as I told you, the camera is not the sophisticated one, so we don't have the possibility to control the screen. We just have the live view on the presets angles. But the idea is that when you have the software just for the camera, you can just use the software. You don't need to use it with our application. So it's independent from the concept. The other feature is that we can fly to any of the presets point that were put it now on the mission. So I will just fly here, and I will fly to another point back to the on the mission. So we can just fly now to any point that was previously uploaded to the drone. We can also during the mission change the mission. So I can just put any new waypoint on a course or anywhere near the drone. And I will just put the new waypoint somewhere here in the middle, right? And so we can now just make the drone fly to a new point that was preset on somewhere in the area that was supposed to be monitored. And we can see that the drone is just flying there, and it will also stop and wait for another command by the operator sent to do some new things, right? So the drone is already on that point, and we will just return home. Let's say the mission is completed, we can return home. I click the return home command. The command was sent, and the drone should now return back to the landing spot, and we will see how the landing procedures go. And after the drone reaches the landing spot, we can check it. You can check it here. The drone is just up above the landing spot, and you can see my team just moving around the aerial drone. Now the drone just is settled above the ground station, the aerial drone. So the drone is now it's on the height and waiting for the dome to open. We can check if the dome is opening. We are waiting for the signal from the dome just to open. The dome is opening, so the drone will just start the landing procedure in a moment. And it's when I change the windows, it's not refreshing. And now the drone should just get that was the movement of the drone when it's just fixed on the landing area, because we are using the infrared beacon just to position the drone directly above the landing spot. We are doing some researches, as I told you, just to change that into the local setting. So now the drone is landing on the aerial drone, and after it lands, the positioners just moves from the sides and sets the drone just in the middle of the elevator, just to put the elevator down with the drone on that. You can see that here are just positioners moving just to have the drone exactly in the middle of the elevator. You can see maybe on the picture here on the screen that there is the device. This small plug here allows us to charge the batteries in the drone after the flight. So when the drone is hidden inside the dome between the flights, it plugs in and the batteries are charged so that it will be ready for the next flight. The time of the charge is For us, we just said it that it will be just twice the time of the flight, so that we will not just kill the batteries too fast, because when you charge too fast, the batteries will be died earlier than expected. So now the procedures of the landing is done. After the positioners move out, the drone should go down, the dome should close, and the mission is completed, and the drone is ready for the next start. Okay, so I will go back to my presentation. Yeah, as you can see, the drone is. We will see the procedures to the end, maybe, and during that, maybe we have any questions for me about the system, about the possibilities to implement it. Perception. Thank you very much.
So, Mr. Poland, I thank Bartek for his state of the art presentation.
Yeah.
As usual, from the science of things.
It's right at my best.
Thank you. First catch. So tell me please, what system really you use it for generation of the images and for control of flight? What system?
Yeah, the flight controller is not designed by us. We are just using the existing PSO. So we are playing with PSO with the modeling communication that is typical, as Professor said, for that kind of drones. So we are sending the data for the modeling. And we are thinking about our own control system, but it's in the development. No, we just use the state of art, the stock available things. The cameras are typical monitoring cameras, so it's just IP cameras that we have for the monitoring of the aerodrome. And on the drone, we have also the IP camera connected to the, now it's connected to the LTE modem, so it's transferred through the data from the drone is transferred with the GSM data. So that it can just go worldwide without any problems with communication to the ground station. That was the idea, because when we flew further than those 2 kilometers, there was a problem with communications with the drone. And in that way, we just get the data from the drone with the GSM modem constantly on any level.
And your system permit to introduce a flight program to the drone?
Yeah, I just created the mission here and sent it with the modeling protocol back to the drone.
On what distance can you move your drone?
The drone flight time is 30 minutes. So we calculated that it can move from the ground station like 10 kilometers to have possibility to do some mission there and go back. So it's like 10 kilometers radius. We are now allowed in Poland to fly on 2.5 kilometers without additional permissions. That's why it was the circle here you have seen.
And during the flight, you can change the flight program, yeah?
Yes, as you have seen, I could move it from to any point, and I could add another point where it's flew. I can also draw through another mission, and it's just upload. It's hovering, so that's how it is.
Okay, very interesting system. Thank you very much.
Not show the passback, find itself drawn. But I see the passback, it's a straight line, so.
Yeah.
You have to input it in the passback.
It's not flying through the same path. It's flying on the straight line. That's how it was designed.
And so I not have to input the passback.
I just click the return home, and it returns home. If there is some complications with the dome or with the drone, I also have the 2 other emergency buttons. First one is return emergency, so it's not landing on the dome, it's landing on the next to the dome. There is a special place designated for that. If the drone dome does not open or it does not have or it has any other issues. It can land next to the dome, and the land now procedure is just if something is going on with the drone and it doesn't have a possibility to move back to the landing site, it just lands in the plane where it is. So those are those safety features we have.
And you can to introduce the coordinates of the final place of the movement by a computer.
Yeah, that's what I done. It's just setting the waypoint on the map. We are not inputting it just as the coordinates by hand, but it's the user interface putting everything on the map. Yeah.
Please, Natalia.
Yeah, of course.
That's it. How many people, I'm having Zoom said this in Moldova. How many people do you believe have this team to perform this automatic flight?
They were there to prepare the sites, because it was raining yesterday. So they just came to check the system. Of course, there was a guy in the green jacket because for the time we have, it's not implemented anywhere as the automatic flight, so we don't have all these legal requirements fulfilled for the automatic flight mission. He needs to be there just to as an operator, as the manual operator of the drone. But yeah, he was doing that. He was just having the remote controller with him. Just in the case something will happen, he will be able just to take the control in the drone. And that's the legal requirement, so that's why he was there. And the team was there just I told you, just to prepare him to fly. So the idea of the whole auto invent system was that it will be stationary, because now, as I showed you, it is standing here on a trailer, so that we can move it to different locations and perform the flights from in different sites, because it's our prototype. But the idea of the system is that it is stationary, so we just put the dome somewhere, it stays there like forever, and you can ready for flight. So you can the idea of the automatic inventory system was that it will fly frequently on a predefined path. So we, for the purpose of infrastructure protection, we introduced this interface, because the previous interface that did not allow the operator to change the mission. The mission was predefined and uploaded only on specified locations, so that the drone will fly only the missions predefined previously. So that's we just do on the predefined schedule the missions, or it will do the same mission on the call of the operator, because, for example, we need to check today how much call we have, or we need to do it weekly, so we can compare what is the difference between the amount of the call today and how it was the week before. So that was the idea of the project, and because of the input to the infrastructure protection, we introduced this user interface. So that's the new feature we have after finishing this project. We finished the project in October last year, and since November, December, we started to modify it in the direction to infrastructure protection, because we got the question from that company if we can do that for them, because that's something they will need.
Thank you very much. So you can ready past the.
Yeah, the drone is ready. The time we need to if we want to move to a new location, of course, it will be good to have a day before, just to see where we can put it and to have the safety conditions. And the setup time from the time we just arrive on the location and start the flights, like here on this airfield, because we have this airfield where we perform those presentations at our test flight. So from the time we arrive till the moment we are ready to fly, it's like half an hour, just to set up the weather stations, the cameras, and everything else. So it can be done like you can imagine that you have the system on a trailer. So then you have just one person that know where to put all the stuff. So it's basically the weather station and the camera that is looking from the side, like you can see this picture here. So setting this up and turn the energy on and everything else. So
Thank you very much.
How about, I have one more question.
Yeah.
How about using your system? So you use for coal excavation monitoring.
Yeah.
In Moldova, we don't have excavation, coal excavation, but how about sand, rock excavation? Because sometimes we learn from our government, it's very difficult to monitor this. And there are many situations that people think that maybe it's not monitoring properly. That's very light. Light way. But I think having your system from Moldova, you can very precisely monitor these things, and I think it's very really needed here.
The auto system is capable of measuring anything that has a volume. Because we are measuring the volume, not the amount, but the volume, because you know there is also the density of the stack. So that depending on density, you have the amount of the resource, but the volume we can measure of anything. Like Professor said about the not agriculture, not architecture, it was archaeology. Yeah. So basically, the system is also possible to be implemented in the archaeology, but in the archaeology, you don't do the frequent measurements in the same place. You just do it once, and then you have all the data required. So the idea is that it can perform same flights repeatedly in the same
size, but the volume changes.
Every day, every week.
Despite that the materials comes out.
That doesn't matter. I have the leaflets of the system, so I will just can distribute you just to have all the information I had on the presentations on the paper.
Thank you.
And final question on
Please.
if you can use your drones and your system for military applications, for example, to deliver the first of the bombs, it's possible or not?
We are not we were not thinking about military applications of the system, but we can lift anything that weighs up to 6 kilograms.
6 kilograms.
Yeah.
And supplementary units for carrying the different.
The payload of the drone is 6 kilograms, so we can lift anything that weighs 6 kilograms, and it can fly to predefined location.
And to modify the system to input supplementary buttons to close some mechanisms. It's not it will be just the yeah, it's possible. We are now not implementing this system, but having knowledge from that system. We are doing the system for the board guards. It will be the drone on the cable starting from the car, and it is also, as Professor said, is just the measuring device. So we are just hovering on the 60 meters above the car. And on top of the drone is the antenna, just to get the communication that is happening around. So I'm really interested in the presentation of Luca, because he's also will be talking about that. So getting the information about the radio's locations and frequency emitters around the site. And also there will be the camera on the drone, double system camera. So it will be the daylight and the infrared light of the camera, put it on the drone. So we will fly on different spots with the system, and it will be just one button system. So the operators will sit in the cabin, push one button, and the drone will just start hover and be ready for, because it will be just like the drone itself will not be anything special, because it will just start and land just and hover for 4 hours because of the wire passed from the car, so that it charging.
Thank you. Okay, now we have less time for 1 hour and at sharply at 1:30. Yes. 1:30 we start the next afternoon session. We have for today 4 presentation, 4 online presentation, and the moderator of this afternoon session will be Professor Mislav Perek. So let's have a nice lunch now, and at 1:30 please come back to our conference. Thank you. Thank you. Thank you.
Dear ladies and gentlemen, let's have our after lunch session. And the first report will be presented by Mr. Konrad Wostovic, Colonel Doctor from Faculty of Mechatronics and Aerospace, Military University of Technology from Poland. And topic is UAV flight safety based on modern technology. So, Mr. Wostovic, are you ready?
Yeah, I'm just going to go for online. It's the community positive English here in a lot of I don't know what the same happens to something. It's not answering. It's not answering. Not answering. Yeah. He said that he has a meeting before and he will be short on time. So I hope he will be in a few minutes. Okay, let's wait. That's why he couldn't switch with me. That's why he couldn't switch because he had every part of the day plans and so. Few minutes. Obviously, for there's too many easy for I can see it. Calls. Just because no measures, measures. Yes, no, to jest raz машина. Kiedy ночи скрижился, на злог. Если люди чату НАТО, с острова, майжус, курс. Let's ask машина, а круто большой есть. А что такое? Есть можно да. Ничего. Почти до всего. Есть алтрейдинг professor Ioannis Tampaksis, dar nu e prea și poate să ne poată deja pe statutul законul бывший город реально Vreți să facem să încercăm eu haideți, dacă este gata, încercăm să se întâmple. Chisinau.
I think you might forgot that there is a time zone difference.
I think so it's 1 hour.
1 hour,
late.
yeah.
Yeah, and he might think that
Yeah.
local time.
No, I difference is because he had 1 hour. 1 hour, yeah, that's why he said me that he will be just on time after the meeting, but probably he is on the meeting right now. Yeah. Now I just understood it. That might be the case.
Yes, but now the next speaker is not online, but the other one, the third one, the one is from Greece is online. And maybe it's better to ask him.
Yeah, I think so, because Conrad is not answering, and I think he's on his meeting. Oh, yeah. Yeah, let's do that. I'll write him that he will have us instead of Professor.
Yes, to see if it's possible to switch between this presentation. So necessarily ask him if he's ready or not. It's a complete. Okay. Thank you.
Yes, hello,
Thank you
can
so-
you hear me?
Yes, we can hear you.
So will be announced the reporter. The first one is a Professor Ioannis Templakis from Hellenic Air Force Academy, Greece. And topic is principles of propulsion systems, application on UAVs. So Professor, please start your presentation.
Thank you for the kind introduction. Shall I share the presentation?
or is it already uploaded? Let me check for the presentation then. Just a moment.
Yes, thank you.
I thought I was to present at 3:30, wasn't it?
Yes, but we have a little bit delay with our current presentation. That's why we see you all online. And if you have time, please help us to be on time with our schedule. You can present now, please.
No worries, no worries. Okay. So let me start the presentation then. Okay, is it? Can you see it on your screens? Or not yet?
Not yet.
Not yet. Okay. So. Okay. Should be okay now.
Yes, it is.
Okay, perfect. So let me just close the door of my office to make sure no one interrupts here. So as promised, I have prepared a presentation on the principles of propulsion systems, and I have looked on the applications for the UAVs. I have been teaching propulsion systems since 2000 here at the Hellenic Air Force Academy, and all my studies and research were all focused on this field. So before starting discussing what I have prepared for you on propulsion systems, let me first give you a brief presentation regarding what we're doing here at our academy, and in specific, what we are doing at our laboratory of propulsion systems. So first, we do a lot of studies on mission analysis. You know, we have the privilege as an Air Force, I think all the Air Forces have the same privilege, to be at the same time a user of airplanes, and also to have an academia like the Hellenic Air Force Academy. So we can very easily address to our squadrons, reach the data from our flights, and then do some analysis regarding the profile of usage of our aircrafts. So what you see on those top two figures come from some studies we did regarding life consumption of our engines from various aircraft, depending on the type of mission or depending on the profile we fly the aircraft. So we can gather the results and take advantage of them in order to make our everyday life more easy, and also more and spend less money on that. The second branch of studies and of research is related to our external partners, and in specific Cranfield University, that we have been working together since many years. So along with them, we do several studies regarding the engine faults like fouling or erosion, and we see how this affects the engine life. And then we also, under the umbrella of NATO and support projects, we do very interesting studies on sub-idle gas turbine performance. So this is in brief what we do for our research, and on top of this, we do also have our laboratories that support our studies and our research. Now, let us move to the propulsion systems themselves. So what we are looking to when we're talking about propulsion. So we're looking for ways to create a force on a body in order to mobilize it, to make it move, in order to sustain its movement if it is already moving at a constant speed, or if we need to change it in its direction while it is moving, and this is mostly applied in space. So propulsion systems to us are the structures or the engines or whatever you may call it that are present on the body, on the vehicle, and try to produce this force. In most of the cases, these are engines that we're going to discuss about them, but also it may well be flapping wings. This is also a case where we're trying to produce a propulsive power for our vehicle, but this is a very rare case. So how to make this force? Okay, we all know Newton's third law, everything comes from there, and we also take advantage of the Newton's second law in order to quantify this force, this propulsive force. But then if we try somehow to categorize the propulsion systems, then we may do that on the basis of what do we expel from our vehicle in order to be propelled. So we have the case where we are forcing air behind, or the case where we're forcing hot gases. In these cases, in those two cases, we're talking about air vehicles within the atmosphere. And we have a third case where we're forcing behind charged atoms or molecules. And this applies, as you know, to the space vehicles. So this would be what we are actually forcing behind in order to go ahead. Now, when we're talking about air, we're actually talking about the propeller. We need a prime mover to spin this propeller and push the air backwards. But when we're talking about gases, then in this case, we have two options. We either have, if we're operating within the atmosphere, then we receive air, we energize it, and we push it backwards. Or if we are outside the atmosphere, or even in high altitudes, then we have both the oxidizer and the fuel, and to produce the high energy gases and push them backwards. This is actually the rocket case, as you all know. Now, if we're talking about space propulsion, then the charged atoms or molecules come also into play, as we said before. So we accelerate them in an electric field, produce ions and accelerate them. These are the ion engines, for instance. And in case of the gases, we will only stick to the rocket case since we don't have any air to combust. Now, what you can see here is another categorization of air vehicles propulsion systems that I have attempted based on my experience. You can see many of these, but let me present to you how I see propulsion systems based on the way they produce this propulsive force. So the first big, these are all applied to air propulsion, not space propulsion. Okay, so we have the very first big distinction between propeller and jet. So if we're talking about a propeller, if we are looking how to spin a propeller, then the next step would be what kind of fuel do we use in order to make this propeller move. So if we use not fuel, actually, how do we store energy and where the energy is coming from? So this might be either from the fuel, it might be stored in a battery, it might be coming from solar, from the sun directly, or we can even add a fourth arrow here and talk about wind if we're talking about flapping wings. But again, this is an exception. So if we stick to those three, then looking to the fuel itself, this may be fossil fuel, this might be nuclear fuel, this might be hydrogen fuel. In the case of fossil fuels, I do also have in there all the synthetic fuels. So in that case, if we're talking about a fossil fuel, then we may have a turboprop, an internal combustion engine, a hybrid engine, if we put some batteries on the side, or a detonation engine, or even a direct combustion engine, which is the most usual. When we're talking about nuclear, of course, we produce heat from the nuclear reaction. It's just one way to do so, but it's very rare to use nuclear power for propulsion systems. There are some projects going on, but they're well classified, so it's not a popular way of propulsion. And then we have hydrogen, which is very, very in fashion, I would say, these days. A lot of people are talking about hydrogen nowadays, and they're talking either in direct combustion solutions. I'm talking mainly about manned aircrafts, or through fuel cells. Then, if we follow the jet arrow, we have either a breathing or a non-air breathing engine. So if it's a non-air breathing, we're talking about rockets and the two types of solid and liquid fuel. Or if we're talking about air breathing engines, there are the four basic types of gas turbine engines. So this is an air vehicle propulsion tree. I think that's a way to include all possible propulsion systems out there.
Hello, Pasquale. Hello?
Okay, can you hear me now?
Yeah, hello. Hello.
Or you can move to our next presenter.
No. It's your presentation, still your presentation, Johannes.
Okay, so for some reason I lost connection from my.
Yes, we are waiting to be reconnected from your side. In our case, everything works.
Okay, so I connected through my phone, because for some reason my PC.
We see you and hear you very well.
Okay, then, so let me continue, but you cannot see the presentation, I guess, now.
We can start your presentation from our computer because you emailed me your presentation. So we can present from our computer here in the room. Is it okay?
Okay, yeah, please do so, and I will have it on my screen. So if you can move to slide 9, and this
just we will start the presentation.
Okay.
So can you see now the presentation?
I can see. Let me. So no, I cannot see it. To be honest, it's hard for me to handle this through the mobile. Yeah, here it is. Perfect, good. If you can move to slide 9 then.
9, go,
Yeah.
we go to slide 9. Just say next slide and we will follow your speech.
Okay, thanks. Next slide, please. Okay, so these are our races. So what I mean with races, can you hear me clearly?
Yes, we hear you.
Good.
Very well.
So our race to conquer higher speeds in propulsion systems took us from the internal combustion engine to the turbojet, the ramjet, and then finally the scramjet. This is what we have as technologies as we try to run faster and faster. Then our race to conquer higher altitudes started from internal combustion engine. It all started there actually. Then we had the turbojet. Then as this air gets thinner, we go to the rocket, and then finally to the solar or the ion propulsion. Then regarding our race to conquer higher range, endurance, fuel economy, etc., for high subsonic flight, always here we're talking, we started from turbojet. This is what the airliners are using. Then we have the turbofan of bypass ratio up to 5. Then we move to the ultra high bypass ratio turbofans, what we have now. And I think we're going to soon see again the turboprop plus the high-speed propellers, what came out during the previous fuel crisis, where we were looking at the NASA rotors, those well-designed rotors that they could spin at quite high subsonic speeds, 0.7, 0.8 Mach. And but then they were abandoned because the fuel was not too expensive. So we stick to the turbofan. Those engines might come again into play. Also, the engines like the open fan, etc. And then we lately have also the hybrid versions of the engines in order to manage the electrical load of the engine. As far as the long-haul aircraft are concerned, I don't ever believe we will move to the battery or to the full electric engines, but we may do so for short-haul or medium-haul aircraft. Then regarding our race to conquer the environmental performance of the engines, we started from the internal combustion as always. Then we started playing with some variants of the engines to improve our efficiencies. Then we looked at combustion chamber improvements like the stage combustion or the lean premix combustion, etc. That was about 2000 at that period. And now we're looking all together in the three. What you see there on the right side of the slide, the distributed propulsion of small fans distributed along the air around the aircraft, the fuel combustion we expect to have, or the synthetic fuels we expect to have a lot of reduction in CO2 from there, and also the hybrid versions. Can we go to the next slide, please? So I'm sure you have seen several slides like that in this conference. It's the way we classify UAV vehicles. I'm not going to stay on that. It's just there for the completeness of the presentation to have these data readily available regarding how we classify UAV systems. So let us move to the next slide directly. Now, regarding propulsion systems for UAVs, where we are now. So based on my literature research, I've seen that you can see the graph, the pie chart on the left side. We mostly use what comes easily out of the shelf, which is a piston engine, an IC engine. And then we try all other types of engines. You can see it on the graph, but at a smaller percentage. The truth is that it's not viable to invest money on developing a propulsion system for a UAV. It has really happened. We actually take engines that they already were flying. If it is for a big vehicle, then we take engines from manned aircraft. If it is for a small vehicle, then we might even use engines from modeling, if it's a very small vehicle. So we very rarely see attempts in designing an engine from the start. But we do some studies that I think it worth the effort to start looking a bit more closely and be more careful in designing propulsion systems specific for UAV. So on the slide that follow, I have gathered a few principles regarding this, and I try to compare the design of propulsion systems for UAVs against propulsion systems for the classical manned aircraft. So if we move to the next slide, please. Okay, what we have to remember when we design propulsion systems for manned or unmanned aircraft as engineers, there are those three very basic principles. The first is that our forward speed should be the closest possible to the propellant speed, to the speed we expel our propellant, whatever that is. We need that, as you know, to have a good propulsive efficiency. Then the second thing we need to have always in mind is we want to have the least possible and most efficient energy conversion. And this comes when we start to think about batteries and motors and solar energy and this and that. So there we need the least possible conversions to keep a high efficiency. And then we start thinking a lot nowadays, and we'll be thinking more and more on the days to come, to minimize our carbon footprint and in general our pollutant generation. Then along this, on the side of these criteria also comes the cost of production, etc. What the guys from the procurement or from the economic department would think about. But what you see here is mostly for the engineers. Can we move to the next slide, please? So the question is there a shift in design philosophy when we're talking about UAVs? I think there are some very distinct differences when we think to design propulsion systems for unmanned aircraft. The first is that the design space is much bigger. We can start from a manned aircraft, the size of a manned aircraft, to make it unmanned and propel it. So it's like aircraft we're used to fly around. And we can go down to very small vehicles, as I say on the second point. So the design space is huge, really, and becomes very complicated. The second important thing is that the airworthiness rules are not affected by potential loss of passenger human life. So a good thing, although I'm not a specialist on airworthiness, on the rules, I mean, they apply. But I would think that the rules would not be that strict, and we won't have to prove new technologies to the possibilities we need to have for critical parts in the case of engines that go to manned aircraft. We're not seeking for values 10 to the -9. And also, the mission requirements can be quite inventive. So if you have a pilot in there and you need to keep him alive, then you cannot overdo it with the mission requirements. But if you have an unmanned vehicle, then you can prescribe whatever comes to your mind for this vehicle to do. And this will make it very hard for the person to design the propulsion system to cope with. Can we move to the next, please? So I believe our design philosophy, the flow chart is the same, can't be any different. So we define the mission, what we want our vehicle to do. We describe the mission in engineering terms, endurance, speed, range, etc. And then we start to design both the propulsion system and the vehicle while having in mind the production cost and the carbon footprint. This is a typical flowchart for propulsion system design. But now, when we're talking for small size unmanned vehicles, as you can see on the right, then we need to have a lot of exchange of info between the guy who designed the aircraft and the guy who designs the propulsion system. What it used to be for a fighter aircraft up till now was the engine guy would like to know where the engine would be placed and also some stuff about the intake and how this might interact with the rest of the aircraft. But that was about it. And it won't be that much interfere with the guy who designs the aircraft. But in this case now, it would start to think about distributed propulsion, small fans up and down and around the vehicle. Then we need a very strong, there will be a very strong interaction between the two departments. We do have all the self-propulsion systems ready now for unmanned. So this comes also on the table. What was not the case for fighter aircraft. You know that when a company wants to develop a new aircraft or wanted in the past to develop a new manned aircraft, would go to the people who make the engines, announce his intention, and then even 10 years before, or even 5 years before they start actually producing the aircraft, and they would tell them, please try to think of the propulsion system for the aircraft that I'm going to make in 10 years from now. In this case, as I said, we may also pick an engine from the market very easily. In small size unmanned vehicles, the choice of the propulsion system is no longer obvious. What I mean by that is that if we have a long-haul aircraft, a new long-haul aircraft, we know for subsonic travel, we know the turbofan would be the solution. But in the case of or other cases, but in the case of a small unmanned vehicle, you have too many choices for the propulsion system, how to spin the propeller, for instance. So again, the thing becomes more complicated. And finally, we do actually design engines for our aircrafts based on takeoff and on the end of flying performance. We need actually to optimize between those 2 points. But for unmanned vehicles, you may have too many points that you need to look at for your engine design. So you can see there are a lot of differences that appear in the design philosophy. And we move to the next slide, please. So if we try to make a flow chart, that one may follow in designing a propulsion system, I think would look like something like that. The first thing to question yourself is if you want to fly supersonic or subsonic. If you want to fly supersonic or at very high altitude, then you need a gas turbine. And you have to choose between the standard types, turbofan, turbojet, ramjet, scramjet. If you want to go subsonic, then the options are too many. You may go for internal combustion engines. I like to see gas turbine engine as an internal combustion engine. I don't like this linkage that the ICs are only the piston engines, because gas turbines have also internal combustion. Anyways, so if you go for an internal combustion engine, then you may need, and you have a low mean takeoff weight, then you have a small vehicle actually. Then you are looking at the piston engine for the better thermal efficiency. But if you want a high takeoff weight, then you need to consider the gas turbine engine and specific the turboprop. On the other side, you may go for an electric motor and have a lot of choices from there how to spin your electric motor, how to move your electric motor. So if we move to our next slide, please. Regarding gas turbine engine, this is the this is the, can you hear me? Can you hear me? Sorry, because I had an incoming call. Sorry for that.
Yes,
So-
yes.
Okay, so for the pardon? So for the gas turbine engines, for the gas turbine engines, as I was saying, we have the classical graph. Are you saying anything? I can hear you with interrupted voice. I hope you can hear me. Just a few slides to conclude. So okay, then for the gas turbines, we have this graph you can see on your right, which is the well-known graph for gas turbine engines and the ramjet, turbojet, etc. You can have a look at that. But I would like also to stress out we do have those options, what you can see here on the figure. Use the SOC fuel cell in either direct in the combustion area or linked, or what you can see on the figure 19, as I said, direct to the compressor. So there is an option to use a fuel cell. This is the end for the propulsion of the gas turbine engine. So if we move now to the next slide, if we're talking about internal combustion engine, as I say there, we may use liquid hydrogen combustion in order to make our engine green. But we should keep our mind stable, what we have below, that we need to lose endurance and range. I think a lot of technologies will come along regarding hydrogen, and this will be also introduced to the UAVs. And then if we can go to the last slide, please. Now, regarding the electric motor, I think this graph says everything. What you can see there is that on the top, on the y-axis, we have the energy density, so how much energy can we carry on board, and on the x-axis we have the power density, how fast can we discharge this energy and use it. So if we need endurance to stay for many hours on the air, then we go to the top right left corner, which is the fuel cells. We have a very big range of batteries to cover all the power, almost the entire power density range for high energy density values. And then we have the capacitors that they have very big power density, but they usually can store a small amount of energy. So that would conclude my presentation. I hope it came out well to you. We'll be happy to answer any questions. In the meantime, I can see that internet is back to this issue. I will stay tuned till the end of the session to answer any questions you might have. These are the references. Thank you.
Thank you very much. Questions, please? No questions. Thank you very much, Professor.
Thank you. Thank you, sir.
Domnul Ceama Да. Если гада.
Hugo passa de Silva.
Hello?
Oh,
Hi, can you hear me?
Professor Hugo.
Yes.
Okay.
Professor Pasquale, great to see you.
So the next report will be presented by Professor Hugo Placido da Silva from Institute Superior Technical University of Lisbon, Blackstone in Portugal. So the topic is remote sensing for biometrics and health and novel opportunity for unmanned systems. So Professor, please present your report.
Okay. Are you able to see my screen?
Yes.
Perfect. Okay, so good afternoon, everyone, and thank you very much for the invitation to present at the event. It's a great honor for me and the team to participate and maybe to follow up on some joint work after the lecture and after the event. My team is affiliated with the Pattern and Image Analysis group in Lisbon from the University of Lisbon, in particular the Department of Bioengineering, and we are one of the leading universities in Portugal in the field of engineering. From our group, we also have a number of spin-off companies, one of which is Plux, that works in the field of biomedical engineering. But I would start my presentation exactly through by a short presentation of the group, then showing some of the work that we have done on the field of wearables applied to control of drones, in particular, a few projects that we've done in this area, and then moving on to some more forward-thinking ideas, in particular regarding an approach that we call invisibles for health sensing, and that can be used with drone-based remote sensing, in particular video-based measurement of health parameters. Just a short overview of what we do in our team. So we are based out of Portugal. IT, Institute de Telecomunicações, is one of the largest private research facilities in Portugal. It's a state-owned laboratory and a state-sponsored laboratory that has the mission of transferring knowledge to the industry, and this is done a lot through collaborations as the one that we can establish from our presentation here today. Within Portugal, we are one of the largest centers, so we have more than 360 researchers working full-time with a PhD, in a total of a team that includes more than 540 researchers countrywide. And some of the outputs that show our performance in terms of applied research include, for example, patents, which we have an output of 10 patents per year, more or less, and also in the creation of added value positions, in particular through spin-off companies, from which within the center we already established 12 companies from research that was co-developed with some of our team. The lab has multiple facilities and multiple sites across Portugal. In Lisbon, where we are based, we actually have 2 sites, but then we have other sites in Coimbra, Porto, so all the main universities have a presence of IT, and we work as a network of researchers countrywide, so we can expand the capabilities of our team in Lisbon with knowledge from other researchers in other sites. IT is organized in different knowledge areas that range from basic sciences and enabling technologies to networks and multimedia, optical communications, wireless communications. Our group in particular is focused on biosignal acquisition and processing, machine learning and AI applied to biomedical sensing, and development of novel devices, both wearables and invisibles. We will see in a moment what this means. with the goal of developing research of practical utility for the medical domain. So very focused on health monitoring, biometrics, and related applications. In essence, we are more focused on the technology. So we develop essentially industrial and enabling software and hardware technologies that then are applied to clinical support, well-being, and human-computer interaction. And so here on the field of unmanned systems, we can see very practical applications on well-being, human-computer interaction. And so we've been touching a little bit the problem on these two domains. Our work has been recognized both nationally and abroad with multiple awards. The most important was in 2017, one of our developments being recognized as the most relevant industrial and enabling technology in Europe by the European Commission Innovation Radar Award. And so it's another indicator of the work that we developed and how it has an impact beyond our lab. We are very well positioned in terms of scientific output. We have hundreds of publications across the senior researchers in the team. We are also very actively involved in projects, both European, with industry, with public authorities. So we have a good performance in that domain. From our lab in particular, we have already 4 companies that came to life based on cutting edge research developed here. And we have a portfolio of 12 active patents, so not submitted, not pending decision. So these are patents that are active and licensed, sub-licensed. So we really focus on creating added value to the partners and the teams with whom we work. And so we are quite collaborative. We worked with a number of research centers, companies all across the world. So we have here a few examples of collaboration with academia, also with industry, big and small companies alike. And our researchers are placed also in top level names in the industry. So we have a relevant platform also for training. In the scope of the talk today, I will show a little bit the progress of biomedical sensing and some of the ways in which we are contributing to change the paradigm and to make new approaches possible that can tie very well with unmanned remote sensing systems. And I will start with a very practical use case, which is monitoring cardiovascular activity, because cardiovascular disorders are both related with health, with the psychological side of the human being, and cardiovascular disorders in particular are still the leading cause of death worldwide. And so it's a problem where we have a big emphasis in the work that we do. And biomedical sensing was actually quite scaled up or quite incentivized precisely by cardiovascular disorders. And this is an example of an early implementation of an ECG monitoring machine that in 1924 actually was the base of the Nobel Prize that was assigned to William Eindhoven, which has done a very practical and deep characterization of the electrophysiology of the heart, defining not only the measurement methods, but also how the signal could be interpreted and used with clinical validity in the real world. And so this actually opened the door for large-scale deployments of biomedical sensing systems, which have evolved greatly over the years. And now this is a typical device that we see in a hospital, in a clinic, to monitor a 12-lead ECG, but that has been also the focus of significant improvements in the sense that these type of devices requires very specialized knowledge, that requires high learning curves or long learning curves, and that also has a high cost associated with the operation and also with the acquisition of these devices. One area that has seen particular development has been the area of wearables, as we all know. And so there's been historically an attempt of making part of the functions that are available in a medical device that lives in a clinical facility or in a hospital available in form factors that the person more conveniently can use in their daily lives. And this is an example of a development that was done here in Portugal, in Aveiro in particular, that's called Vital Jacket, where the ECG sensors in this case are integrated in the fabric of a shirt, and whenever the user wears the shirt, he can have an ECG monitored over a long period of time. One of the problems with wearables is the fact that they interfere with the comfort of the person. So if you see this t-shirt is very tight to the body, and so it in a way may not be comfortable for people to use on a regular basis. And so there have been some hindering factors to the adoption of wearable devices that motivate the search for alternative approaches. More recently, the ECG in particular has been proposed in wrist-worn devices, and so this is an example of the Apple Watch. There are others, but it's an example of the Apple Watch, where the person uses the watch, and whenever it touches the watch with the opposing hand, it can measure a single lead ECG. But still, these devices are in a way not usable at scale, in the sense that people need to wear them, people need to charge them every day, people need to be able to buy them, and so they have also some bottlenecks that in a way prevent their widespread use, not to mention the fact that in the case of the ECG and the Apple Watch, the person actually needs to do a voluntary gesture, so it needs to touch the watch in order to obtain the signal of interest. And so although we have done some work in the area of wearables, and this is an example of a device where we are using actually a different signal, in this case is muscle activity and motion, as a controller, in this case for a drone. Here it's illustrated in a toy problem, but we can do a gesture-based control of the aerial drone, so we can control its movement using a more natural interaction with a device, so without having to use an actual controller. And we have also replicated this for land-based terrestrial drones. In this case, we are again using muscle signals measured in the forearm alongside with motion data, and using this as a control modality to a terrestrial drone. Here showcased also on a toy problem, but that can be deployed for other real-world systems. And so in this case, we can detect a gesture, so turn left, turn right, move forward, and then in the end we have a special gesture to trigger a function that the drone has, which is the ability to jump. And so we can have a multi-degree control of the device. Although we have done some work in the field of wearables, more recently we started to think differently about the way to obtain these measurements, and understanding that on one hand, there's a limited real estate to the amount of devices that we can put on the person, which are many. So we put an armband to control the drone, we put a wristband to measure the ECG, we put a smart glass for the person to see augmented reality input near the head, we put a band to monitor respiration. So we always think about putting more devices on the person, and this has a limit to what we can do, and in not so short time span, it's easy for people to start looking more like a cyborg than an actual human, which led us to the possibility to integrate sensors in everyday life objects in a way that it is the object that has the sensor and not necessarily the person. And so one example of one such device is this one that I hope you can all see in the video. So we have this type of device that was developed here at the group, and one example of what can be done with the invisibles, as I can show you, is precisely this. So I have the device turned on without having one particular sensor on my body, but instead just by touching the electrodes that are here on the device, I can start the acquisition and see in real time an ECG live coming from my body. So you can see here that I'm very happy to be here giving this talk. So my heart rate is quite accelerated, but I'm still alive. So you can see the periodic heartbeats in the live chart that come just from the interaction with this device. And so this set us in a path that I would say transforms quite significantly the way in which physiological data is measured, and also the way with which people interact with sensing devices in the perspective of well-being, quality of life, assessment, and also control. So using these signals to control other systems. From the moment in which we have the ability to touch an object and monitor the ECG, there are multiple possibilities that arise. This is one example of such an integration. So this shows the device that I've just demonstrated integrated in a computer keyboard. And as the operator is using the computer, we can monitor the ECG, and from this signal, derive heart rate variability, and other metrics that enable not only the assessment of health on the user, but also the assessment of mental health or concentration parameters that are related with the sympathetic nervous system. So from the moment that we have the sensors integrated in objects, there's a whole world of opportunities that arise and that we've been developing over the past decade in terms of research beyond the state of the art. So this is one example of integration of the exact same approach that I've just shown in the demo. This is another example of the sensor integrated in a steering wheel of a car. This is a project that we've done for Nokia for one of their business lines that focused on road safety and mapping business that includes a road safety app in some countries, where they wanted to understand fatigue of the drivers while they are doing their job as professional drivers. And so one of the requirements was not to change the look and feel of the interface with which the driver interacts. And so here you will see that we have a textile-like material, this honeycomb structure that appears here, and where the driver is holding the steering wheel. It's a conductive fabric that we are using as an electrode, so it doesn't change the look and feel of the actual steering wheel, but it enables the electrical connection between the subject and the sensor. On the center, we have a color-coded scale that the driver can use to mark his level of fatigue, because we were collecting ground truth data also to develop the algorithms. And here, in this particular case, using heart rate variability features, we were able to detect at a very early stage the convergence to a fatigue state or the relaxation state of the driver that enable him to perform his mission fairly well. And so there was a high correlation between heart rate variability features and the self-reported fatigue from the driver. This is another example of such an integration. So the sensor here in this case integrated in the remote controller of a PlayStation. It could be any other remote controller. So the person holds the controller with both hands, and the gaming station can be monitoring the health status and the concentration of the person in real time. So any object that can be functionalized with these sensors can be used as a biomedical sensor without requiring the application of a specialized sensor on the body. One problem that comes with this approach is the fact that the typical clinical data is all very clean, so anyone that has seen an ECG more or less relates with this type of signal. When we change the interaction with the device, we get another layer of problems that is related with filtering, detecting what is a valid signal and what is not a valid signal. And so here is an example of the type of signals that we obtain with our invisible ECG approach. That includes power line noise, motion artifacts, triboelectric noise that is intermittent. And so this led to the development of what we call a knowledge extraction pipeline that includes filters that have been tested to work with these signals, KRS detection and feature extraction algorithms that have been validated to work with these signals, and then machine learning methods that enable us to do outlier removal in a fairly consistent way, and then extracting meaningful information that can then be used by a classifier to produce a decision on the health status of the person or on the emotional or homeostasis of the person. So we have a knowledge extraction pipeline that enable us to go from a very contaminated signal to useful information, either for quality of life, interaction, or well-being in general. This has been validated comparatively to medical systems. This is an example of our measurement compared to a 12-lead ECG. And what we can see both visually and numerically is that the hand signal is very well correlated with the lead one of what we get with our with a medical grade system. And here we are using the cosine distance measurement bit by bit. And we can see that lead one, the Philips device lead one, is very well correlated with what we get at the hands with our device, even numerically for a high number of participants that were assessed. More related with the diagnosis, we've been developing also artificial intelligence techniques. In this case, we are using quite extensively autoencoders to determine compressed representations of the data from which we can derive a classification. And here we have some results for the classification of atrial fibrillation from ECG data. So we use the actual ECG waveform as the input to the classifier, and then in the end we have the classifier automatically detecting what is normal sinus rhythm, atrial fibrillation, and we can get this with above 80% accuracy. And these are not even the most recent results that we have, because adding the heart rate information to the feature vector that we train the encoder on increases the performance by 8 to 10%, and so we have very good results using these approaches, and they've been validated also in existing data sets. One area that we've been working on also is to detect the person using physiological data. So instead of adding more sensors to a given setup, we focused on understanding to which extent can we use physiological signals as a biometric fingerprint to distinguish different users. And here we can see even visually on the bottom right matrix of charts, we can see in orange the curves, the individual heartbeat waveforms for a given subject, subject B and subject A. And in black, we have the average of all these individual curves. And in the dashed line, that it's barely noticeable, we have the standard deviation. And what we can see even visually is that there is low intra-subject variability, and there is inter-subject variability that, in a way, are two desirable properties to do biometrics based on physiological data. And what we were able to determine, this was actually a work done with Professor Anil Jain, which, according to Guide to Research, is the #1 scientist in the world in the field of computer science, electronics, and in particular biometrics, according to Google Scholar. So he is a co-author to this work, to which he actively contributed. So this is being curated by high individuals in the field. And the performance that we get for a population around 60 subjects, these are the results, is in authentication, so a one-to-one problem where we want to verify the identity of someone that claims to be a given user of the system, we can get recognition rates around 97, 98%. In identification, where we only say, here's an ECG, who does this ECG belong to, we have recognition rates between 94 and 95%. So it's quite comparable to what we get from other soft biometrics, and so we can get quite competitive results. This we've been pursuing in a more optimized way to develop an edge-based processor to do the biometric function directly on the device, so preserving the identity. In particular, we are using an approach that's called binary convolutional neural networks, where without degrading the performance of the system, we can have high gains of computing, so we can have speed ups to 3 orders of magnitude comparatively to standard approaches. These are some of the results that we obtained in this approach. And so it shows a little bit what we can do from signals collected with sensors integrated in the object. This is a simple example of the whole system working. So we have the keyboard that measures the ECG, and then we have the detectors working in background and matching the identity to the database. But it's just a practical demonstration of how it all ties together. This is another example of deployment of the system, in this case in a vehicle of shared use, where the problem here was how can we confirm that the person that is going inside the vehicle behind the wheel to drive matches the person that is authorized to drive this vehicle. And so here there is a first stage of enrollment or authentication that is done through an RFID card. And then with the ECG system working on the steering wheel, we have the center console of the car collecting the ECG. Here it appears with a very low amplitude, but the ECG is being recorded by the vehicle. And when it is able to verify the identity of the user, it unlocks the features. So we have like a two-factor authentication using the ECG as a modality, in this case in a demonstrator of a shared use vehicle. This is a patented technology, and a spin-off company is currently exploring this technology. But so it's I think an interesting part of our work. In terms of other pathways that we are following in this invisible approach, so this, as you've seen, still requires an interaction between the device, the sensor device, and the user. It alleviates the need to have something on the subject, so it's already one gain comparatively to the point where we are now. But we believe that there are other approaches that may even be more advantageous, in particular video-based sensing, which ties to remote sensing, drone-based remote sensing systems, in particular following this video-based contactless physiological data acquisition approach. And here we have some work that is studying aspects like psychomotor retardation based on eye blinking. So we have facial detectors that are available off the shelf, but that we then use to compute eye opening metrics that are illustrated here in the bottom of the image, and from which we can derive eye blinking rates. And this is then relatable with lentification, psychomotor retardation, and degradation of performance while the person is executing certain critical tasks. And so this is an example of our detector working in real time for a database of videos that is publicly available and with the performance already validated in this domain. Another area is also related with the psychomotor retardation is using head movement, so using head jerk in order to monitor the stress state of the person. So this is also ongoing work where we are focusing our attention. On the physiological measurements, we are using video-based heart rate monitoring. This is an example of video-based photoplethysmography, where we can segment the forehead, cheeks, so large areas of the skin in the face that we can use to monitor the variation of some color components, which is highly influenced by the cardiovascular dynamics. And here we have an example of a remote PPG sensor based only on video that could be mounted on a drone to monitor the physiological parameters of the person in real time. And of course, from the moment we have a robust detection of the cardiovascular peaks, we can derive not only heart rate, but also heart rate variability, which is here illustrated, both heart rate and heart rate variability, more on the emotional content of these metrics. So here on the bottom right charts, we have the heart rate for a task of appreciation, where you can see a regular pattern that is normal for the heart rate at rest. And then you can see, for example, for frustration, high variability of the heart rate that doesn't follow the regular pattern for this user. And then here on the left, you can see a chart with a spectral analysis of the heart rate, in particular the ratio between high frequency and low frequency components, which is related also with emotional stress or emotional arousal of the user, and that in particular was part of the system that was used on the Nokia project that I mentioned before to detect driver fatigue. And so all of these can be computed from videos collected on remote sensing devices, either drone, aerial, terrestrial drones, or others that can capture the footage. I was a little bit ambitious on the time, but I'm reaching the end of the presentation. I would like to end by acknowledging some of the institutions that have been funding part of this work until now, and also thank the team of researchers, both senior and juniors, that have been involved in this project throughout its different stages. And I would like to thank you for your attention and be open for questions that you may have regarding any of these topics. Thanks again for the invitation.
Thank you very much, Professor. Questions, please. So it was very profound and from different points of view. I have some questions regarding different applications of possible systems.
Mm-hmm.
So for the first one, as the first part, you presented application of sensor to control different mobile systems,
mm-hmm.
movement mobile systems, okay? So how many instructions or commands can be generated by this kind of the sensors to control by the mobile devices?
Mm-hmm.
How many instructions?
Mm-hmm. In this case, so far the implementations that we have enable us to have 3 control signals with EMG, so we can have left, right, and then a third gesture. But we haven't explored this in use cases where we need more gestures, because we have 1 degree of freedom, which is increasing the number of sensors, which enables us to have more control signals coming out of the system. But based on the muscles, we have 3. And then based on the accelerometer, we have an additional 3. So we can control moving forward, moving backward. We can also tilt left and right, and then move up and down. And so there are still a few commands that can be extracted from this system to control third-party devices.
Okay, thank you very much. Another question. So the sensor used for based on finger cardiograms identification. Okay.
Mm-hmm.
So what is the correctness of this kind of applications?
Mm-hmm.
How correct
mm-hmm.
will be identification of the person?
Thank you for the question. So this is actually pioneering work that has been done by our team. It builds in previous state-of-the-art where chest-based ECGs were used. So we already had the hint that there is a potential to this method of authentication. It doesn't scale as much as, at least to our best knowledge, it doesn't scale as much as the fingerprint or iris recognition, which are called hard biometrics, so systems that work in the limit for thousands of people. So we don't have data for thousands of people yet. We cannot assess the performance in that domain, but our intuition says that the system doesn't work well at scale. Nevertheless, we are not proposing it as a replacement of current biometrics. The most recent results that we have show, for example, that for a group of 60 people, we can have 98% recognition rates in identification for 95% recognition rates for identification in a group of 60 people using 5 seconds of data. So it's already quite performant for some use cases. And for authentication, where we know a claimed identity and we want to validate that identity, we get then recognition rates above 98%. So, but this for a group of a few dozens of people. The question is that in many use cases, you may not even have that many people. So if you only have a critical system that is accessed by 10 people, you want to recognize those people very well. And as I mentioned, in the perspective of not being a replacement to existing biometrics, but a complement, our system can overcome severe limitations, for example, from biometrics. Biometrics still using fingerprint. So fingerprint still today has a major limitation in what concerns forged templates. So the silicon fingers and the liveness detection are problems that the fingerprint cannot recognize by itself, and adding the ECG as an extra layer can greatly reinforce the security in a multi-biometrics approach. Facial recognition also, despite the progress that it has done, it's still not perfect in what concerns artificial replicas. So the 3D face scanning is already an improvement, but this doesn't overcome the problem, for example, of silicon replicas of the face. And so there are multiple hindrances that still affect the more established biometrics. So seeing the ECG as a complement to this is a way of enhancing the security of the system with an additional layer that is intrinsic to the person and very difficult to forge from a picture, from a replica extracted from a surface with which the subject interacts with. I hope to have answered their questions.
Thank you very much again. Thank you.
Thank you.
All the best for you.
Okay, bye-bye. Thanks.
Bye. Signor Moldova.
Actually, is one of the state is one of the your proposal to presentar. Presentar.
Allora, primo quadrato. Yeah, now it should be the coffee break.
Coffee break.
Coffee break, and after the coffee break. Yes, so yes, good idea. So thank you very much. So we'll have the coffee break until 3:30.
Yes.
Yeah. Thank you. Great. Thank you. Okay, dear ladies and gentlemen, let's continue our session. And the first speaker is Mr. Konrad Kostovic, Colonel, Doctor, and Faculty of the Mechatronics and Aerospace, Dimitri University of Technology, Poland. And the topic is UAV flight safety based on modern technology. So, Mr. Colonel, please start your presentation.
Good afternoon, gentlemen. Let me start my presentation. Okay, first of all, it's really hard to explain how much I wish I were there with you, because you know I'm dedicated to your team. There is some issue with speakers because I can hear myself, but I hope that maybe you can switch off the microphone. Okay. Can you see my presentation?
Yes, it's clear and it's visible.
Okay, so again, I would like to be there in Moldova with you, but actually it was the only week in this year which was absolutely not accessible for me, so I'm so sorry. Hello again to all of you who knows me, and to them who don't know me yet, a few words about me. I'm an Air Force maintenance officer, so my military background gives me some points which I can be aware of dangers which drones in any kind can bring to the modern and temporary world. So, at the Military University of Technology, we conduct projects and research not only on drones, but also on anti-drone systems. This is why we are aware of all the danger which is around us and which can be brought by the drones used intentionally in the aggressive way. Further, I was trained as a maintenance staff, aircraft maintenance staff, and all my course, all my field of study was dedicated to maintain aircraft. And the awareness which I trained in this time was that there is no aircraft which can be considered as a toy. So for me, each aircraft, even that which you can buy in a supermarket, can be somehow dangerous, somehow working incorrectly in the ecosystem of the airspace. Further, you have to be aware, and we all know that the big military drones are really big aircraft, yeah, and are airplanes or helicopters, which maintenance should be considered as maintenance of the ordinary manned aircraft. Of course, somewhere behind, we have regulation, which gives us proper dividing of the groups and the proper separation of that kind of unmanned aircraft. And we'll pass this topic in a few minutes. Then I am also a software developer, and I had a training on the software dedicated to airspace and software dedicated to be embedded on board of aircraft. So the danger which comes with the software part is inevitable if we design the software not following the rules which are prepared especially for aviation. What are the rules? Of course, it's a standard DO 178 with a proper version, because currently it's version C. But following the standard can help us avoiding the misleading use of that software in a future application of our system. Starting with the regulation, as we know, European Aviation Safety Agency, which covers all the national agencies, provides us with a particular regulation dedicated to drones. Currently, we are somewhere near to the end of this procedure, so we are after January the 1st, where all the national authorization should certificate and declare fully conversion of the national systems to the new European Union system. But we are just at the edge, which is other milestone, which is the point where all operations in the open category should be conducted according to the European Union regulations, and all model clubs and associations should receive an authorization by the national aviation authorities. But we are still far before the final point, which is that all operations in the open category are conducted according to the European Union regulations. So we are somewhere after the major milestone, which was following and complying the European regulations by national agencies, but still not at the end. But this stage means that the national regulations shouldn't work anymore in European countries, of course. So all the points which were specific for national areas should be unified, and we should comply only regulations implemented and imposed by EASA. And what the regulations are? We have 5 groups. So the aircraft are divided into group C 0, 1, 2, 3, and 4. And the groups are by the weight of the aircraft and by the application of the aircraft. And here we have what I started with, introducing myself and my aircraft maintenance staff background. The group toy aircraft. Of course, the regulation says that there is toy aircraft group T0. It's an aircraft lower or lighter than 250 grams with a specific maximum airspeed, and the purpose of that aircraft is just buy it from the supermarket, buy it at the supermarket, and just start with it, start playing with it. Of course, it is not my intention saying you that it's not true, because it's really hard to arm someone or destroy anything with such a small aircraft. However, as an Air Force officer, I would be very, very aware of putting it into airspace, and I would be very careful in calling it a toy with full consequences. Because for me, everything which flies, which can fly, can be somehow or is somehow a part of this environment. So, of course, we can buy C0, we can use it without any other consequences, low consequences, but we still have to be aware that it is an aircraft, because it's a toy, but a toy aircraft. Of course, moving to other groups, all of them require a specific course and specific preparation of the pilot. And the preparation follows the regulation and depends on the class of the drone. And again, the same classes with some other kind of options which decide of the class which the drone is connected to. And again, we can see that also the class 0 is here, and also this class is connected to the following operational conditions. How can we understand the classes and the conditions which are presented, which are connected to the classes? So this picture can show us how it really looks like. So the open category with A1, A2, and A3 drones is within 120 meters height and without any other specific environmental requirements. So we don't consider flying beyond visual line of sight. We don't consider flying over the crowd or over the buildings in the city. If we do, we can use this open category only in visual line of sight. Of course, all the other categories should be used with the specific conditions and specific courses of action presented and strictly described in the EASA regulations. With each drone, which we can buy, we get a leaflet. The leaflet is standardized, so each drone bought in any European country should have a leaflet which looks in a similar way. And the look of this leaflet we can find in the regulations on the website. We can get familiar with it, and not only can, because during preparing for license, we have to get known what is inside the leaflet, which is delivered to us with any drone. So the way of presenting information is standardized and should be clear for any customer, for any user or future user of the drone. Why are we doing that? What are we fighting for, actually? Well, we aircraft specialists, yeah, and any guys who ever used drones or ever used any aircraft know that there is something like segregated airspace. So the airspace which we cannot use without restrictions. We have to follow some regulations to use that space. Considering military drones, you can say, okay, forget about this civilian regulation. You have dedicated area closed for civilian aircraft. You can fly. Okay, you can fly as far as you can do that on or over some training areas, which is actually closed for civilian aircraft, for civilian traffic. However, there are, as you know, military aircraft, military unmanned aircraft too, which has to be implemented into civilian airspace. This is why the countries implement military regulations which allows moving military aircraft, also drones, into segregated airspace. Of course, we are not here to scrutinize how this segregated airspace looks like and what are the particular classes of the areas and degrees of connection and degrees of access to the classes and to the areas. Just leave it this way, that there are the classes and there are the connections between the areas which are controlled or segregated in the specific way. Of course, we know that the areas are mostly around the airports, airdromes, but also around some specific areas which are not free to fly. This is some example from Polish airspace and only some of Polish segregated areas which are not freely open for flight. Of course, the segregated airspace has a lot of people inside which are there to control the traffic inside. For manned aircraft, it has been done for years, we can say manually. So the pilot connected or talked to the controller, and this way the information was passed. However, using the modern ways and modern means of communication, we can do a lot of things automatically. And we can do it passively and actively. So flight control radars can follow the aircraft, and other way, the aircraft can inform controls about position and about intention. How about unmanned aircraft? Well, we have no opportunity to do it in this analog way, in this manual way, because there is no pilot. Of course, there is a pilot operator on the ground, but it is not possible this way as with this manned aircraft. This is why the automatic systems has been implemented to put this control in this automatic way. There are only two examples of software which can follow the drone and in the same time connect to the control station, connect to the air flight controller, and report the current position of the drone together with the current position of the pilot operator of the drone to the flight controller. So it's all about information. It's all about fast way of passing information from the drone by the drone pilot to the flight control. The applications are operational, they are implemented into flight control system, and they work. We call that geo-awareness. So it means that we know, we as controllers, we know where all the drones are. And the new regulation imposes an obligation to the pilot to use one of the systems, automatic systems, to report the position, of the operator and position of the drone operated by the pilot. It gives controllers a powerful and effective tool for controlling traffic of the drones and to implement drones traffic into the manned aircraft traffic. But if a controller and if the system knows the position of the drones, we can go one step further. And we can limit the drone and the pilot of the drone from flying there where the flying is not permitted. Where is it denied, and we call it geolimitation. So using the system, we can limit the drones against flying in the areas where they are not allowed to fly. It is about regulation, about the overall general capabilities of the current systems. And now I want to say a few words about how to do that. So what is behind on the side of the drone and on the side of the controller, and how it can work this way to do it and to operate it in this way. So first of all is an autopilot, which is a controller of the drone. But currently available autopilots give us a lot more capabilities, because actually these are not only autopilots but also navigation systems and the control systems for our drones, which gives us the capabilities and the abilities of the main control computer known from manned aircraft. Of course, there are many solutions of autopilots available worldwide, and we all know them from our own experience because we use them in our application. So this is this main part of the system, of the drone system, which gives us control for all other equipment on board. What we need for sure in this autopilot system is position. The main source of the position is global navigation system or systems, because there are a few of them available currently. And again, it's so common that it's not a point to explain how the global navigation system works. More interesting can be what we have GPS or GNSS denied environment. It means that the GNSS signal is not available for us. Can we still set our position? Well, let's start with the systems which give us some boost to our GNSS positioning. So we consider that we still have some access to the signal from the satellites, but we want to do it more precise. The best known way currently is ATC, which gives us access to some pseudo-satellites, which allows us to set position with a very precise way. And here again, you have two options. You can use your own ATC antenna, where you set your own satellite on the ground in a specific position, or you can use ready-to-use pseudo-satellites around you, connecting some system, just buying the access to this ATC positioning. So there are two opportunities. Both are similarly detailed, similarly precise. But GNSS signal, both coming from the satellites or come in the space or coming from the satellites on the ground has some vulnerabilities, has some disadvantages. The main are that they are the signal is very weak and is very vulnerable for spoofing, for other interference. It is very suspicious for the cyber attacks, is atmosphere dependent on the area where we want to get the signal, so it can be mirrored by the buildings around. And again, we all are aware of that disadvantages. This is why many of us work on the systems which are GNSS independent, so which can work completely without GNSS signal. And the first of that is SLAM, simultaneous localization and mapping. It's a way of navigating using images, using pictures taken with a camera mounting on the object and connecting the consecutive images determines the position and simultaneously determining position, it builds a map, which gives us a better awareness in the area, better situational awareness, and it also increases our drone's precision, because the drone going back on the same path is more precise, navigating in this previously mapping area or environment. There is a lot of applications and a lot of algorithms available currently, and there are embedded devices more and more capable of implementing SLAM, because in SLAM the biggest issue is hardware, which has to be properly programmed and properly prepared for working with the algorithms, because the algorithms are heavy for the power consumption, not electric power, but computational power consumption. There are also other systems which will be mentioned in a few minutes, and it all gives us the way to the picture, which I really like. Actually, I like a lot of pictures which give us a lot of details. Let's stop for a while with this picture. Let me give us a pointer. Okay. So in this picture, we can see the legacy elements of the sense and avoid system. So it's an ordinary connection, because between the control area and control station and the aircraft. It's, as you can see, a line of sight link. It's a satellite communication, which is with us for years. But we connect ADS-B, which is something which also is with us for years, the automatic defense surveillance broadcast, and which allows aircraft to talk to each other. But also, we add sense and avoid techniques, which give us more opportunities, which give us more capabilities. And these sense and avoid systems use all the sensors on the aircraft and implement it into the common network. So the current sense and avoid technologies use not only the most modern techniques, most modern technologies, it connects all which is available currently. And this is the main power of this technology. One of these is TCAS, Traffic Collision Avoidance System. These systems were implemented many years ago, and they allow the aircraft connect to each other and talk to each other with the high precision. And after the connection between aircraft, they can talk to each other about the future and the intended action in the near future. Next, the TCAS systems give order to a pilot in the manned version or to automatic autopilot in case of unmanned aircraft. So TCAS system can be successfully implemented into the unmanned airspace. Sorry. Automatic dependent surveillance broadcast. It's always with us for a while now, and it's also a part of the modern sense and avoid system. It works in phases. So first, an object detects an intruder. Then it starts tracking the intruder. Then the system evaluates a potential collision. After the calculation, it prioritizes collision potential, how probable it is. Then it declares action which is required to perform. Then the system determines an avoidance maneuver. So what I have to do to avoid a collision. Then it commands the maneuver and then proceed to execute the maneuver. Of course, the system also connects aircraft. So one aircraft with ADS-B is connected to the other one. So the aircraft know which is going to do which maneuver. It's similar to TCAS, but it's much more sophisticated. Okay, let's move to some custom applications and custom solutions. Not only us, but also our research focuses on LiDARs, which are a perfect source of information for any unmanned aerial vehicle, and actually for any vehicle. Are high precision, high resolution, high speed. So what's wrong? It still costs a lot and it consumes a lot of power. Thankfully, we have smaller and smaller LiDARs, and they are cheaper and cheaper. So we can use them in even small drones and implement successfully our algorithms. Another sensor which is very useful and sometimes even inevitable in sense and avoid systems is a radar. It detects low altitude objects and it operates in all weather conditions, but it can be easily interfered by electromagnetic source of energy, and it don't track well accuracy when the target is clogged. And again, the power consumption is high, and the previous radars were quite big. However, here again, we have smaller and smaller radars with lower and lower power consumption. So it's very optimistic, and we already have some examples of using radars on even small drones. What we all know are sonars, are cheap, light, compactness, and the only disadvantage is range and a kind of surface which they operate with. So they work actually only with a flat and upright environment. So as you know, we can use it in this final approaching. And then what I've already mentioned, saying about SLAM, simultaneous localization and mapping, electro-optical systems. So putting it simply, cameras. Yeah, we have cameras with some imaging processing units, which gives us a lot of capabilities, not only in tracking, but also in localizing and in mapping. So also this branch, this area, simultaneously with LiDARs, are in our most attention. Then infrared sensors, which work at night, are not affected by electromagnetic interference and have capabilities to detect obstacles in some pretty considerable range. And it also gives us a map of surrounding areas, surrounding obstacles after processing the image. And then quite pretty similar thermal imaging, which detects heat and operates in all weather conditions unless it's covered. And for covered equipment, for covered obstacles, it can give us a view which is not available considering the light visible cameras. And at the end, examples of small drones implementing sense and avoid systems with multiple sensors. So in this small scale with NVIDIA processors, which are dedicated to processing data from cameras and other sensors, and the big scale integrating all what we can imagine. So IFF transponder for identifying friend and foe, ADS-B receiver, radar, and TCAS on board of unmanned aircraft. Thank you for your attention.
Questions, please? No questions? I have the question. Do you have the question? Okay.
Could you turn up the microphone because I can't hear you?
It's about GNSS systems. Can you, yes, can you estimate how often we can we have this problem, and what should we do to avoid this problem with GNSS system vulnerability? Different factors that influence this vulnerability of GNSS research. We can use this control. What should we do?
I've heard about the problem, yeah, but it was the only what I've heard, yeah, the problem with GNSS, yeah, yeah, but again, what is the problem?
How often we can use, I'm sorry, how often we do with this problems with GNSS signal?
How can we detect the signal, or how can we spoof the signal? How can we detect?
Yes, if we lose the signal, we can't detect the signal. What should we do?
Well, when we lose, this is let's analyze the case. There is an UAV, yeah, flying, and the system is prepared for get the GNSS signal from satellite, yeah, and the drone currently don't have any GNSS signal from satellite, yeah, and your question is what to do, yeah?
Yes, because we need safe flight. What to do?
Yes, so this is the intention of the second part of my presentation. So actually, currently, there are no drones with the GNSS dependent only systems. There has to be any other way of navigational information. And what are the information? RTK is not the point here because RTK works only when the GNSS signal is available, so it can complement the GNSS signal. When you have signal from the satellite, then you add the signal from RTK and it gives you better precision. What you can use when you don't have GNSS, the first answer is inertial navigation system, but it works only in short term. So you have ready-to-use module for GPS INS systems, but how it works? It works only when this GNSS signal is available. So you can use it for calculating the precise location, the precise position of your drone, only between the incoming signal from GNSS. So if you don't have GNSS at all, INS, the current INS is not an answer. Because it's not the kind of INS as we know from, I don't know, Su-22 aircraft or MiG-29 aircraft. There were huge gyroscopes which allowed us to work without GNSS. The same is with submarine. Yeah, there are gyroscopes which gives position to the submarine without GNSS because there is no GNSS at all. Yeah, in a submarine. But our aircraft INS GPS systems actually don't work without GNSS. Sorry. So what is the solution? The solution is only in this our newly came approach newly came ways of positioning or setting location. So SLAM, simultaneous localization and mapping. So you can use cameras, you can use LiDAR, and even you can use radar in some restricted conditions to determine the point of cloud, which gives you the first step for determining position. So this is an answer. Yeah. So the sources of information can be various. Again, it can be picture, and here you have also a few options. So it can be a picture from ordinary camera, it can be a picture from infrared sensor, it can be a picture from thermal camera, but it's still a picture. It is processing in many various ways. It's first moving to the grayscale, then it's it's not the point here to describe the process, but it's some sophisticated process. And the process is not only sophisticated, but also computing power consuming. So you actually can't do that in most of your embedded computers, which you have available on board of your drones. You need something really powerful, and that powerful solution, the powerful option is NVIDIA computer. Actually, it's one of a few available computers which are able to cope with SLAM currently.
Thank you very much.
Thank you. And another question. So in your report, you mentioned that the drones of the classes C0 and C4 or toy and model do not need the registration. So they cannot be registered. Okay.
I said that they should be registered according to the current regulation.
So they do not, they can be registered, yes, and can be used.
They shouldn't be used without registration.
Yeah. So tell me please, how dangerous are drones for aircraft, helicopters, etc.? How dangerous are?
Well, all the aircraft, even the smallest one, is extremely dangerous for any aircraft because the parts of the aircraft, especially the parts of the engine, and the best example is turbo engine for modern aircraft, is very vulnerable to any object coming into the intake of the engine. So this is why the aircraft areas and the areas of the aerodromes, of the airports, were the first areas which were interested in the anti-drone systems. Actually, not military, but the civilian airports, because even the toys, as we said, so the drones which you can buy in every supermarket, were an extreme danger for the airports. And the drones flying around the airports in the space where the manned aircraft could be in some moment, in some place, was unacceptable because of that danger. As you know, even a small bird inside the engine going through the inlet of the engine can pose a danger for the aircraft turbo engine. So let's consider a drone, even a small drone with hard carbon or metal parts, yeah? You never know what can happen. It can be mixed by the turbine or by the fan, yeah, but it can also harm or even destroy the first parts of the turbo engine.
Thank you very much. Another questions? So, Dr. Gurtovic, thank you very much for your very good presentation. And we hope you do successes in this area.
Thank you very much.
And the final is ready. It's ready. I'm waiting. Asking us from start. So, final report today will be presented by Professor Janusz Litkowski and Professor Romuald Waszylski from Gdynia Maritime University, Poland. Marine equipment and the marine drones, problems of using and positioning, assessing and order of its accuracy. So please, who will present?
Jest wszystko. I teraz jak włączyć?
Thank you, Mr. Chairman. May I start with my presentation?
Yes, please. Yeah.
Jak pan wrzucił?
My presentation is entitled Marine Equipment and Marine Drones, Problems of Using and Positioning and Assessing of its Accuracy. The presentation is prepared by Janusz Mindykowski and Romuald Waszylski from Gdynia Maritime University. My presentation basically is based on two chapters. The part one is related to selected problems of using marine equipment and marine drones. This part is mainly based on the literature review. And second one, problems of positioning and assessing of marine equipment and marine drones. This part is mainly dedicated to the case study initiated by our university team. In the first part, for selected problems of using marine equipment and marine drones, I will present shortly three subsections: marine equipment and marine drones, selected problems of using aforementioned devices in the studied area of the shore and the seabed, and methodology of measurement to illustrate the studied area of the shore and the seabed. In the second chapter, related to problems of positioning and assessing of marine equipment and marine drones, I will present problem to solve, applied algorithms and metrological properties of the related measurement instrumentation, accuracy analysis of the measurement results, case study-based evaluation of uncertainty for TLSE method, and finally, methodology of accuracy analysis for UAV method. Final conclusion will be summarizing those presentations. Unmanned aerial vehicle, speaking about general characteristic of marine equipment and marine drone, you may differ many kinds of drones, and among of them we may, for instance, find as easy available on the market fixed wing drones, drones with several horizontal propellers, as well as a fixed wing drone that is capable of vertical takeoff and landing. one of the most important general characteristics of the drones under consideration are the payloads, which enable to include, for instance, electro-optical, infrared, and multi-hyperspectral cameras, radio and light detection and ranging, and particle gas sensors. The use of drones for tasks in a coastal and maritime context over the ocean and the near ports are one of the most important challenges. And in my presentation, especially the part 2, is addressed mainly to the applications on the over the sea areas. The drone characteristics, there are, for instance, divided dependently on the drone type as multi-rotor, fixed wing, single rotor, and fixed wing hybrid. And among the features, we may find in many positions of the literature, for instance, pros versus cons and utilization. Some examples are illustrated in the table. Speaking about features of the marine equipment and marine drones, 4 attributes can be distinguished. And to categorize unmanned aerial vehicles, those attributes are flight altitude, endurance, range, maximum takeoff weight. But except of those main attributes, many others are also classified by many positions in the literature of the subject. Some of them, like class, category, weight, radius of mission, speed, and example platform, are illustrated in the table below. Examples of current drone capabilities are illustrated in this diagram, but the main point is the payload weight in the function of the range of operation. Examples of current drone capabilities, examples explicitly related to the flight time, are illustrated in this list. I would like to add that from our point of view, I am speaking about research team of Gdynia Maritime University. We were using the position listed as 4 DJI Mavic Pro because of the some advantages represented by this product. Communication technology is an important part of the UAV, and this is responsible for data distribution between system elements and to external units. The very simplified diagram of communication system is presented on this illustration. The elements are for the data input, modem, transmitter, amplifier, and after that, for the data output side, we have a receiver and modem. Communication system types used in the area under consideration may be as follows: command and control, payload link, air-to-air communication, voice relay, transponders. The possibilities of remote control over UAV are ground control, semi-autonomous, fully autonomous. Some details are presented in the slide. Management of drone operations. the management of drone operations in EU law, the division of drone operations is related to the risk of flights for the ground occupants and other airspace users. These are open category, special category, and certified category. UAVs are the best solution for, if we are talking about application of those equipment, carrying out inspections and calibrations, transporting on-demand supplies such as documents, spare parts, medical equipment, or medicine, pollution detection, monitoring, border and illegal activities control, traffic control support, SAR mission support, validation of key infrastructure, operation of quasi-autonomous water beyond and aerial drones within offshore port services, and others. The other applications, more detailed description of them, may include remote inspections and other maritime tasks of UAV drones. It was exposed in the slide. From the point of interest of our research team, especially the border, coastal, and offshore control are in most important mission, but not to prevent illegal immigration, but rather for control technical conditions of the coastal and offshore zone. We may also shortly characterize autonomous underwater vehicles and autonomous surface vessels. The wireless navigation techniques may include GPS positioning at the surface, inertial navigation system using depth reckoning based on depth sensors, inertial sensors, acoustic Doppler current profiles, and Doppler velocity lodgers. Acoustic ranging using acoustic beacons with known positions, sonar simulations, localization, and area mapping based on distinct object and or bathymetric features. Autonomous underwater vehicles as well the autonomous underwater vehicles may contribute such very important features like sensing, autonomy, acoustic communication, and networking. The same kind of features may be also considered in the context autonomous surface vessels. Also, sensing, autonomy, and communications and networkings are properties which characterize of kinds of object. Other important aspects of both categories, as described before, are important technology, endurance, robustness, miniaturization, legislation. All of them are very important for using of this kind of object. But several barriers that prevent the offshore and maritime industries to fully benefit from drone-based technology may be appointed. These barriers are important. We are talking about selected problems of using aforementioned devices in the studied area of the shore and the seabed. And to aforementioned barriers, we may include the harsh offshore environment, places strong demand demands on the quality of the technology and the ability of the drone pilots. But especially, I think the harsh wind conditions, turbulence, and the influence of salty seawater are important ones. Speaking about small drone technology providers, we should take into account the experience that money often falls short. Delays in technology development is provoked by this reason. A way to overcome this barrier is for customer firms to invest in small provider firms and thus help speed up the technology. The European Union regulations continue to develop in support of drone operations in the maritime domain. I think it's very important from the sector that I am a representative. I am talking about of the maritime sector. The most important limitations of the use of UAVs are limited operation time due to its battery power, difficulties during operation in poor weather conditions, less ability to handle heavier loads, risk of hacking, safety and security depend on operator skills, privacy put at risk, national and international regulations still in progress. Now, I would like to try to introduce some words into methodology of measurements to illustrate the studied area of the shore and the seabed. Two technical solutions. It means unmanned aerial vehicles and unmanned surface vehicles enable the investigation of the selected coastline phenomena in two basic geospatial aspects. Firstly, photogrammetric, designed to assess changes of monitored area, exempli gracia in the beach surface relief and the coastline course. Presented a later on case study will be related to this category. Secondly, hydrographic, aimed at determining the seafloor relief, the amount of material sand accumulated in the vicinity of the investigated object, exempli gracia pier and the marina, and the level of increase in its volume as a function of time. This is very characteristic, for example, for the tombolo phenomena. In view of the depths of less than 1 meter prevailing in this region, it's recommended that a hydrographic unmanned survey vehicle be used. During measurement, USCV used two independent positioning systems. Firstly, system consisting of low-cost multi-GNSS receivers. According to the instructions, the accuracy of determining the position of this device is from 3 to 5 meters with the level on confidence 0.95. The second positioning system was the Trimble R10 geodetic receivers, and the horizontal accuracy of the position determining is from 3 to 5 centimeters with the same level of confidence P equal to 0.95. In view of the elongated surface nature of the beach under measurement, it was necessary to plan and arrange an appropriate number of sites. The measurement was taken with a Trimble TXC8 laser scanner without the photo-taking option. Hence, the obtained points clouds had only colors resulting from the calculated laser beam reflection intensity. In view of the small number of the characteristic object to be used for the recording of a point cloud in the field at a later time, spherical tags located in the sand in a manner ensuring the stability of their position were used. the tax had to be located a relatively short distance from the neighboring measurement sites. Therefore, they were located halfway between them or in their immediate vicinity. The location of the laser scanner measurement sites is illustrated in figure 1. Next, photogrammetric flight path was performed using a DJI Mavic Pro drone independently for each of the adopted parts. The data were recorded using PIX for the capture mobile application. During the mission, 621 photographs were taken at an altitude of 660 meters above the drone takeoff level, the beach. Now I would like to start with second part of my presentation. It means problem of positioning and assessing of marine equipment and marine drones problem. Contrary to the first part, based mainly on the literature, this part will be based mainly on our research experience. The aim of positioning is to determine the X, Y, Z coordinates of investigated terrain points. It means continuous cartographic monitoring in this area. Assessing for the needs of this presentation corresponds to accuracy analysis of measuring X, Y, Z coordinates of investigated terrain points and is understood by the authors as an estimation of uncertainty in relation to carried out measurements. The geodetic and hydrographic measurements of X, Y, Z coordinates of the investigated terrain points are presented in the figure when the function epsilon in function X is explained in the next slide. Taking into account this picture, we have in the block diagram sister under measurement, in this case the shore and the seabed under given investigation, measuring system methods and instrumentation. We will consider UAV unmanned aerial vehicles, USCV unmanned surface vehicles, TLESE terrestrial laser scanning, plus PLE national system for positioning in Poland, and supported by DSP and dedicated software. In the output of this block diagram, we have digital terrain model, X, Y, Z coordinates of investigated terrain points. It means positioning, and after that, assessing, understood as the accuracy analysis. In other words, estimation of measurement results uncertainty epsilon in function X. The minimum version of the proposed meta model of measurement includes such components as mathematical model of sister under measurement, mathematical model of data conversion, and mathematical model of data reconstruction. I think that's a very important point based on this concept is that it could be considered that the propagation of uncertainties through those models is a principal operation underlying the procedures for evaluation of uncertainties. In accordance with this approach, in the vast majority of practically important cases, those models may be decomposed into elementary algebraic structures on the form epsilon equal to function X, where vector quantity X, a vector of variables modeling the sources of uncertainty. Epsilon is a variable modeling the quantity whose uncertainty is to be evaluated, and Phi is a function describing relations between aforementioned variables. Aforementioned analysis concern two methods used for creating a 3D beach model. Firstly, using images from unmanned aerial vehicles, UAV, and secondly, based on geodetic laser scanning, TLS, terrestrial laser scanning. And finally, TLS and UAV point clouds are originating from the measurements using two measurements methods taking into consideration. TLS method, applied laser scanning method, the Trimble T8 laser scanner was used, concerns the measurement coordinates X, Y, Z of the investigated terrain points. This method shows a very good accordance of measurement results with mandatory system of geographic coordinates. Measurement results obtained in the local system are transferred to the PLE 2000 national system. Accuracy of the final data results depends only from the laser instrumental accuracy and accuracy of the reference points localization, that is, the points which were used to transformation into PLE 2000 system. Taking into consideration these diagrams, we have the delta TM in the left side and delta PLE 2000, and those segments are used to extract UTLS, it means uncertainty of the considered method. And this uncertainty will be used further as a reference point to algorithm of the UAV method. In the discussed TLS case study, the detailed inaccuracy component of the applied scanner measurement are equal to inaccuracy of laser Trimble T8. It was 1 centimeter horizontally and 1.5 centimeter vertically. Inaccuracy of satellite receiver RE10 used to determine the coordinates of reference point 1 centimeter horizontally and 1.5 centimeter vertically. Inaccuracy of the PLE 2000 system 2 centimeter horizontally and vertically. A cloud of TLS points after georeferencing to the PLE 2000 national coordinator system was a reference data set. It was a very important underlining. The cloud of points obtained from the UAV processed photos was georeferenced as well to the PLE 2000 system. In practice, the sequence of operations realized on the basis of UAV photo data does not allow to achieve a satisfactory level of accuracy of the data on the investigated area. It's really a restriction for this UAV method under these conditions. In the considered UAV method of terrain imaging, the pictures processing operation resulted in the generation of cloud containing more than 20 million points, which translate into a density of approximately 170 points per square meters. In the discussed UAV case study, the detailed inaccuracy component of the applied unmanned aerial vehicle are equal to camera pixel resolution 2.25 centimeter, inaccuracy of a UAV position in the X and Y axis a few meters, in axis Z several meters. UAV method and its improvement. To estimate the quality of the UAV method measurements, it's proposed to use the TLS data cloud as reference data. These data are obtained in the same area as the data in the UF data cloud. Then it's possible to estimate the systematic X, Y, Z coordinates errored components in the UAV cloud as well as their dispersion. In other words, noise in relation to reference value. Now, looking at the picture and this slide, we have on the left side the module from algorithm of the TLS figure. So it means that we use this algorithm for TLS method, and output of this algorithm will be now used to the algorithm for estimating the accuracy of the UAV method. We also have cloud UAV, cloud TLS, and finally, those modules give us possibility to obtain data processing comparison, and from data processing comparison, we obtain delta and U are parameters, absolute values of occurred errors and related uncertainties. Finally, these uncertainties will be accompanied by analysis of uncertainty for TLS method, and finally, based on both those blocks, we receive uncertainty for UAV method. Results of executed measurements of the terrain geometry are treated as random variables. That is, they are subject to statistical rules, and the probability calculus is used to assess them. The term metrological aspects in this presentation concern the estimation of uncertainty in relation to the carried out measurement of the shore and the seabed under investigation. Measurement results obtained with use of the aforementioned method, defined as TLS and UAV respectively, created a series clouds of measurement points. Each of them has different reference in the X, Y, Z coordinate system. In consequence, it's possible to estimate an uncertainty of determination of space coordinates of each measurement point in cloud with applying the methodology of type B uncertainty determining. We are talking about the type B related to guide of measurement. Uncertainty of type B for this case and related uniform distribution give us the expression that standardized uncertainty of the type B is equal delta x, the maximum permissible error threshold value, divided by root mean square from 3. USC from X is standardized simple uncertainty. Taking into account the measurement parameters characterizing the measurement instrumentation used in the described experiment, we can calculate complex uncertainty, taking into account all components used in the measurement procedure. Based on the literature of the subject under consideration, an analysis of the positional errors of terrestrial laser scanning data based on 3D data can be found. The 3D point positional accuracy of every point in the space was analyzed, among others, by the conventional method, modular error analysis. The point position error is a vector with 3 Cartesian components, one for each axis, X, Y, and Z, and denoted delta X, delta Y, and delta Z respectively. The modular error, delta M, is the magnitude equivalent to the square root of the sum squares of the previous term. We are talking about the geometrical sum. Similar approach is presented in the literature related to the discussed theme. The standard deviation of the positional error of any point in the cloud, taken as the representative parameter of positioning quality, is simply given by this kind of the geometrical sum, where the standard deviation in the x, y, and zeta direction is delta x, delta y, and delta z respectively. Now, for a given component, the type B extended uncertainty, UBX, is expressed as UB of x is equal k multiplying by UCX, where k coefficient on extension coverage factor. Usually, from the practical point of view, we use coverage coefficient equal to, which correspond the confidence interval approximately equal to 95%. Equivalent uncertainty, UBE, of the given point position in the space may be calculated as UBE is a geometrical sum of the components related to the corresponding components x, y, and z. First of all, the detailed uncertainty of the components can be analyzed and calculated for the method TLS and related to its measurement instrumentation. Now, I will try to present case study-based evaluation of uncertainty for TLS method and later on for UAV method. This first case for TLS method, the components considered are a reference system TLS accuracy, satellite receiver airtime maximum error, PL 2000 system errors threshold values. They are appointed as USC1, USC2, USC3, and finally the complex uncertainties you see related to x coordinates, x, y, and zeta are given by the presented below equations. Of course, all components are related for complex uncertainty in the components related to coordinates x, y, and z. They are simply related by those expressions. Now, for calculate the given case study, we prepare the uncertainty budget. I think the method is generally known, so we take into account in uncertainty budget the quantity in coordinates x and epsilon. Independently, the uncertainty budget was taken from the coordinate z, and finally we receive the results for the maximum errors for this coordinate and probability distribution assumed as uniform. We receive value of standard uncertainty, approximately USC1 equal 0.58 centimeters, USC2 the same value, and USC3 1.15 centimeters. A complex value in coordinates x, y as equal 1.41 centimeter. The same issue solved for the zeta coordinate give us result. You see complex standard uncertainty equal 1.68 centimeter. Based on the literature of the considered issue of all the aforementioned inaccuracies component, USC1, USC2, USC3 are characterized by the uniform probability distribution and non-correlate each other. So we can assume the normal distribution of combined uncertainties. Based on those assumptions and corresponding received values, and also coverage factor k equal to has been chosen, we receive finally by the formulas presented below for all coordinates the expanded uncertainty UBX for TLS is equal 2.282 centimeters for X and Y coordinates and 3.36 centimeters for Z coordinates with the same confidence level P equal 95%. Now I'll try to present some our reflections concerning UAV methods. Speaking true, we have no already results for this UAV method, but I would like to present methodology because we create a full methodology how to do it, but the detailed our consideration, detailed calculations all the time are under construction. But what can we consider and what can we state now? The UAV terrain model is easy to create with much less workload and lower cost than using the TLS method. Since the accuracy of the UAV method model is far from the expectation, work on improving it has begun. Feature works, this time it's the works under consideration, cover the carrying out, conducting in-depth comparative accuracy analysis of the 3D beach model being created using programmatic measurements derived from UAV when adopted as reference model derived from measurement using a laser scanner. The point cloud obtained from the TLS method can be used to assess the accuracy of the UAV method and to correct the systematic errors that accompany it. Software being developed for UAV measurement accuracy, now I would like to say this, is developed, but on the types we are working for further detailed calculation, and these developments give us possibility to evaluate accuracy assessment and data analysis in several steps. Those steps are programmed in the algorithm implementing, organizing point clouds, sorting by X, Y coordinates, random noise filtering, determining standard deviation within selected areas, UAV, determining systematic interactions by comparing UAV and TLS data, correction of point Z coordinates, presenting the results of the assessment and their analysis. And those steps are planned in this kind of algorithm. These circles in the red color give us the steps appointed before, and taking into account for this diagram, this is the scheme of actions to be taken to improve the UAV terrain model. And through terrain model, we have the 3 steps, 1, 3, 5 in the serious section, another 3 steps, 2nd, 4th, and 6th in the another serial sections, but the both modules are related each other, and additionally, the step 4 of this algorithm is going to the step 5. It means UAV points clouds. The final result, we receive UAV points cloud, visualization of corrected digital terrain model, and the course of uncertainty for specified areas. This is the short description of 7 steps implemented in the presented before algorithm, And I would like to add the terrain model obtained from the raw UAV points cloud is burdened with both systematic and random errors. This is evident in the form of a shift in the Z coordinates of individual terrain points from the reference values and the noise scatter of the Z coordinates of adjacent point. And figure 3 presented before give us procedure for removing both adverse effects. Now I would like to summarize my presentation. Of course, we are aware that it isn't a completed job. Firstly, drones are used because they can reduce time and cost, it's obvious, but they can also ensure human safety and operational efficiency during transportation from port to ship. From our point of view, in the maritime applications, it's important that drones may be applied also in the sometimes danger areas and hostile environment, taking into account the harmful conditions at the sea. Drones can be used also for reducing the carbon footprint when used for over the sea. Also, many other applications are listed here. There are still many barriers to overcome. For instance, improving the distance a drone can travel and its ability to handle heavy and large cargoes. And some developments are all the time provided to improve technical possibilities of the drones. The advancement in the drone system, range, command, control, safety, automation, navigation, and other properties give us a possibility that bring the industry significantly closer to providing lower cost, flexible, more routine, and safer solution to current manned helicopter and fixed wing operations. The industry is now exploring how to combine the technology, drones, and existing airspace infrastructure. Within the next few years, many of the technological barriers will be solved with the focus on technological aid and the integrating drones in more complex and higher risk areas such as maritime environment. In the case of considering research, the error component cannot be linked by a functional dependency, and assuming no correlation exists between components, the accuracy of TLSC measurement is quite easy to evaluate. The uncertainties associated with this direct measurement method have their main resources in instrumental inaccuracies and inaccuracies of the reference data. Since the UAV altitude when taking picture is not exactly determined, the Z coordinates of each point in the terrain model must be reproduced from a series of photos. The uncertainty of the results obtained by the UAV method is more difficult to estimate. These measurements are partly indirect measurements, for instance, Z coordinate. By the propagation function of the uncertainty is unknown, while the X, Y coordinates of individual points are determined directly on the basis of measurement by scaling and matching photos. Z coordinates are designated programmatically as a result of the conversion of two-dimensional photos processed into 3D images accompanied by significant noise effect. An additional component of the zeta coordinates inaccuracy is the low precision in determining the height at which the photographs were taken. It's really the bottleneck of this procedure, a low precision in determining the height of at which the photographs were taken. Thus, the accuracy can be estimated by statistical method and be comparing result with result obtained by another methods, for instance, TLES. And finally, in this article, we are trying to present that the UAV method images is less accurate, but allows the digital terrain model to be made in a relatively short time and with the use of inexpensive equipment. But the necessary condition to succeed the method is to solve the problem of this methodology presented by the described previously algorithm. However, the TLS method, laser scanning, is time-consuming, precise, and requires expensive equipment. For this reason, the aim of the undertaken study is to assess the accuracy and effectiveness of both methods under real terrestrial conditions. And the future, it means, in fact, the current works are organized on the consume the presented methodology in the 7 steps described before. And taking into account this possibility, we are the optimists to solve the problem in the full scale of needs. Now, some references to be used and applied in our presentation. And finally, the authors are grateful to Professor Cezary Specht, research team, Faculty of Navigation, Gdynia Maritime University, for providing us with relating database and results concerning presented case study. Authors of this presentation, Dr. Maśnicki and myself, we are representative of the electrical engineering faculty, and we are mainly addressed to the metrology fields, especially computer-aided aided methods. And finally, I would like to thank you cordially for your patience and kind attention. Any questions? I will be very grateful if you also would and could form the questions for the authors. Thank you very much.
Thank you very much also. So, questions, please.
Unfortunately, Dr. Maśnicki just is in the travel. It was delegation to Cyprus. Just now he is in the air traveling from Cyprus to Poland. So unfortunately, I am alone for with this presentation. I think it would be, of course, very much better presented with the help of Dr. Maśnicki, but it was circumstances outside of our.
So some general questions. The first one, so in marine area, can be used 3 kinds of the drones. So underwater, surface, and flyer. Is correct?
Yeah.
Yeah. So what is the importance of every of which and in the application?
In our presentation, I was trying to explain that finally we are interested in the application the drones as one of the methods to investigate the seabed and relief on the sea. So we was trying to use the laser scanning method and UAV method by drones. And finally, the key point of this presentation is focused on the fact how to prepare the procedure of estimate uncertainties evaluation.
Yeah. So another question, and final one. What influence the speed of drone movement on the accuracy analysis?
I'm so sorry. Could you repeat the question?
Yeah. So the drone can be characterized by the speed of the movement. Okay. So we can speak about the three kinds of drones: underwater, surface, and flight drones. Yeah.
Yeah.
So every of which is characterized by different speed of the movement. Okay. So what will influence the speed of the movement on the accuracy of the measurement or analysis of determination of the coordinates of the drones?
I think that I was trying to present that the uncertainty budget, I'm sorry, it was for TLS, but for this kind, you are talking about UAV. Unfortunately, I have no idea how to completely answer your question. You have only this methodology presented by us as a possibility to obtain the UAV methods, evaluation, and in this methodology, we have 7 steps. The first steps is to make arrangement points, both point clones according to X coordinates. The goal is to find a common area for both point sets. Next, operations are carried out by appropriate sensor in accordance with certain assumptions regarding the resolution of the terrain model in the XA coordinate system. For the adopted resolution of terrain imaging in the TLS cloud, a reference point is determined for each of the distracted segments. 3, while the UAV cloud, the point cloud filtering is performed, and the average of the coordinate for points in each of the extracted segments is determined. Speaking through, we consider that the appropriate software for UAV cloud give us the possibility to point cloud filtering. And finally, this coordinate for points in each of the extracted segments will be determined. And in the next step, using the reference data for TLS, systematic errors are corrected in the UAV points cloud after averaging obtained in operation. In step 6, the standard deviation of the Z coordinates is calculated for each specified factor. Defined operation includes both the visualization of the corrected terrain model and the cause of the systematic errors, as well as the distribution of data errors along the X epsilon coordinates. Finally, I would like to add that for this UAV method, we believe that our software operations done in both clouds of points give us successful solution of the problem. But our data concerning the unsatisfactory results related to height, it means zeta coordinate, were given on the literature data.
Okay, thank you very much, Professor Medikowski. Another questions? No, thank you.
Thank you very much.
This is section. Thank you all of you for your participation. All friends of Professor Delponi. So now it's time to finish today's session, and tomorrow we will start at 9:30. Швидше чекаємо нову 30. Десь по хватило це на 30. Нову 30 по виконанню елементів яричних сала інше. Vă așteptăm cu drag seara care de România.
Thank you very much.